Can you hear me on Zoom?
Yes, I can
Where's
hear
Bob
your
at?
voice.
Or not Bob, Jim. You're up first, right? Thanks, Eric. Since we started late, you can go. You don't have to.
Okay. See, it might be up here.
So it's already on. I would just put that as close to your mouth as she will stay.
I'm not gonna do too much walking around, actually, so.
Up to you. Up to you, wherever you put it. Okay. Are you starting with your slides?
Yes.
Okay. Beautiful. I'll just get that queued up for you. So that's
All right.
all right.
So the velocity.
Start thinking backwards. You should be good.
Hey, can you folks hear me? Okay, and on Zoom? Yes. Okay, good. Start my timer here. Okay, well, good morning, folks. My name is Jim Lewis, and I'm going to talk to you this morning about PiSpeedAS and what it is and what it can do for you. And I'm presenting today on the behalf of the entire PiSpeedAS and Tplot development team. And I especially want to call out Eric Grimes, who's now at SPDF, I believe, Brian Harder from LASP, who really spearheaded the initial development of Tplot and PiSpeedAS. So if you guys are on, thank you very much for your contributions. Let's see, I want to get to my next spacebar. Nope. Julie? Oh. I'm not advancing to the next slide. Okay, thank you. Okay, so what is PiSpeedAS? It's basically a toolbox, set of useful routines that can load, analyze, and plot data from many different sources that are of interest to heliophysicists. So we have several dozen, I think 30 plus missions supported directly with built-in load routines, which I'll be demonstrating today. And what we've done is we've put a fairly standardized interface over all these different data sources and missions and file types to make it pretty easy to just do similar operations to load similar data sets. Now, besides these ones that are directly supported by load routines, there are many more data sets available via HAPI, Heliophysics Application Program Interface. And we saw a demo of that yesterday. And then NASA's CETA web service, they also have a web service. Okay. Okay, how's that? Yeah. Is it better? Okay, awesome, thanks. Yeah, so NASA's CETA Web, they have a web service for locating and downloading data from their various archives. And so PiSpeedAS has wrappers for both of those services. We have quite a few analysis tools for doing various workflows you might want to do on mainly on fields and particle data. We have a simple interface to Matplotlib for our plotting tools. And how this all got started, this is a Python implementation of the PiSpeedAS package written in IDL that's gotten a lot of use. Can I just get a show of hands in the room? How many people have heard of or used SpeedAS or PiSpeedAS? Okay, so some of you will be somewhat familiar. And one of our design goals here was to make it kind of easy for IDL and SpeedAS users to come over and apply their same workflows in PiSpeedAS. So as you go through, you might encounter some things like, well, that construction is not very Pythonic, or these names are kind of weird. That's probably some of the IDL heritage showing through. Okay. So this image shows us sort of the scope of space-based data sources we're dealing with. This is the Heliophysics System Observatory. So we have a whole fleet of spacecraft around Earth, around the moon, between Earth and the sun, and out as far as Mars. And these are all providing very useful data sets for heliophysics. And so sort of the problem is many of these data sources come from different data providers. They're in different file formats. They're organized differently. So one of the goals of PiSpeedAS is to make it easy to access them all in a fairly uniform way, and especially to bring them all into a common environment where you could do analysis, using different data sources and combining them to do useful science. And we work not only with space assets, but ground-based assets. This graphic shows the Themis ground-based observatory network. We have a dozen or so sites across Alaska, Canada, North America. And all of these sites have ground magnetometer stations, and those are very useful to see what's going on in the magnetosphere, especially during auroral displays. And we have access not only to this Themis network, but dozens of other magnetometer networks. So probably by now, hundreds or maybe even over 1,000 different magnetometer sites are available to you in PiSpeedAS. So we have good coverage in the northern hemisphere, the northern Arctic regions, and then we have a few magnetometer chains in Antarctica. So sometimes you want to look at the magnetic conjugate points to what's going on in the northern hemisphere, and then some mid-latitude stations in between. So yeah. So speaking of ground-based observatories, got something cool to show you. This comes from one of the Themis imagers, and this is actually not generated by PiSpeedAS. This is another Python project by Mike Shumko, who may even be on this call. So shout out to Mike for his ASI lib Python package. That's an all-sky imager. That package can deal not just with Themis, but there's also, I think, a network of red line optical imagers from Calgary. And then there's another set of them, I think it's called T-Rex. So his package can show like sort of fisheye views like this, or map them onto project them onto maps in North America. So that's a very nice visualization tool. And I'm just going to run this movie here and show you what was going on. This is the event that we decided we're going to study for this week. This is March 24th, 2023. It's just around midnight local time. This particular imager is from Fort Smith, Northwest Territories in Canada. And you could see we have a very vivid auroral display going on here. And I think it's probably safe to guess that this phenomenon or something like it is maybe one of the reasons many of us got attracted to the heliophysics field. And this is a good motivation to try to understand what is going on, from the sun to the solar wind to the Earth's magnetic field to the Earth's atmosphere to cause these beautiful displays. So, I'll just let this run out. So that was about a half hour of real-time data that we looked at. Oh, there we go. So let's start getting into the nuts and bolts of PiSpeedAS. I'm not going to get too deep into anything really in this talk because there's just not enough time and there's so much to cover. But hopefully I'll give you an idea how to get started using it, sort of skim over some of the important features and concepts, and hopefully show you enough to let you know if you think this is going to be a useful tool for you in your research. So Python requirements, Python 3.9 or above. I do want to mention this companion package that comes along with it. PyTplot, in the IDL world, it's just built in. It's just a component of IDL SpeedAS. But Brian Harder here at LASP started porting some of that code, and he started with the Tplot module. And so that became the PyTplot package. And so that sort of goes along with PiSpeedAS. And then the one thing that's a little confusing, and I just want to warn you off making this mistake now. We've gone through several iterations of PyTplot using different graphics backends, and we've sort of converged on using Matplotlib as the backend. So now we have these sort of dueling packages out there. I just want to make sure you don't make the mistake of in your environment, don't do pip install PyTplot, or things are going to go drastically wrong. You shouldn't have to worry about that. If you do pip install PiSpeedAS, the correct PyTplot package is in there as a dependency. So usually you don't have to worry about it. But you will see, the package name is PyTplot MPL temp, but you import it as PyTplot. So you'll see imports from PyTplot. They are all coming from this version of the package. So after you've done your pip install, the next thing you probably want to do is set this environment variable, SpeedAS data dir. And this is because SpeedAS and PiSpeedAS both can cache the data that they download. So they go out to some data provider, find a data file that fulfills your request, download it to this. Well, by default, it just picks it probably under your home directory. I think it makes a PyData directory. But if you want to have more control over where that goes, it's useful to set the SpeedAS data dir environment variable. And then that also lets you switch back and forth between IDL SpeedAS and PiSpeedAS if you do use both packages. And they'll both be working with the same data cache, which can be kind of useful. So this should be, for the purposes of this workshop, we don't need to install everything that this is all already set up on HelioCloud. But I will show you in the notebooks, I will have a step in each of the notebooks to set the SpeedAS data directory. Probably the most useful thing I can tell you about at this point is where to find more examples, where to find documentation, and how to get help. So our main documentation source is PySpeedAS.readthedocs.io. And those are kept up to date. They're built every time we push to the repository. And so I would say that's probably the definitive documentation source as far as like parameters to individual function calls and so forth. And then we have an interactive help utility. This is something that was requested, something we have in IDL SpeedAS. this PiSpeedAS.libs command. And if you want to do something, but you're not sure what the PiSpeedAS name for it might be, you could pass this routine like a fragment of a function name or something that might show up in the doc strings or a wildcard pattern, and that will return a list of possibly related functions. And I have a couple of examples here. And then in terms of probably the most useful way to learn how to use PiSpeedAS is from seeing examples of how it's done with sort of more realistic problems. So on our GitHub repository, and all these repos are under github.com/speedas. We have several example repositories full of Jupyter notebooks, and probably several dozen of them at this point. So PiSpeedAS examples is where we have sort of more general usage of the tools. And then we have a couple of repositories that delve more deeply into use cases for the Themis mission and for the MMS mission. And you can navigate to these directly in Google Colab. We have it set up that Google Colab can access them. So that's a great way to test them out without even needing any kind of local Python environment or PiSpeedAS installation. The examples we put up on the repo have like the magic built into them to install PiSpeedAS in the Google Colab environment, and you can run it. And as far as I'm aware, everything runs pretty smoothly there. And then finally, if you still have questions or want some help, the best channel for that is probably through GitHub issues on the PiSpeedAS repository. And there you can open an issue if you want to ask a question, or if you want to report a bug, or if you want to suggest improvements, that's the place to go. Any questions so far before I get into running some of the example notebooks? Sean, anything from Zoom? Okay. So we're going to look at 3 different notebooks in this session. Now, these are, if you've already cloned the summer school repository, there should be I forget exactly what it's called, PiSpeedAS, maybe PiSpeedAS notebooks, something like that. And it's probably better if there's a subdirectory under there called output scrubbed, and just to keep a little bit of suspense, those have had the outputs removed so you can see them as you run the examples. So I'm going to try to navigate now to one of my notebooks. Bear with me here for a moment. Okay. Let's see. Let's see here. No, this. No. There we go. Okay, so this is the Introduction to PiSpeedAS notebook. And this is recapping a little bit of the history that I mentioned. But let's just charge in. First thing we're going to do, and this may not be strictly necessary, but we had a late version conflict with the matplotlib package. So we want to make sure that for the purposes of this demo, we get the right version of matplotlib installed, just in case things have been reset overnight. So let's see. Shift return to run this. And it's just complaining about that conflict, but we're pretty sure that's not going to hurt anything. So let's see, shift return. So here is the place. I'm doing this in Python to set the SpeedAS data dir. And we've already populated this directory with some mission data. just to avoid everybody mobbing the data providers all at once as we run these notebooks. And normally, you would probably just have this sort of semi-permanently set in your environment, like if you're on Mac or Linux, you would have that in your shell startup files to set that environment variable, or however you do that in Windows. But for the purpose of this demo, we're going to do this in pure Python with the os.environ call. So do that. So now that is set. And now this is going to be just a very minimal PiSpeedAS example. Load some data and plot it. So first we'll do the imports. So we import PiSpeedAS and we import PyTplot. And then the Tplot program, we're going to be calling that all over the place. So we'll just import that so we don't have to keep repetitively doing PyTplot.tplot. So we'll run that. That's all imported. And as I mentioned, the event we're studying for this workshop is we'll call that the full day of March 24th, 2023. And most of the time in PiSpeedAS, it'll accept dates in this format. And of course, you can specify hours, minutes, seconds, down to fractional seconds if you're looking at really tiny time intervals. And it's pretty flexible. It'll accept just about any reasonable date format. Here we'll just use the calendar dates. And now we'll load some ThemisA flux gate magnetometer data and plot it. So here's the call. Most of our load routines, they're all under PiSpeedAS, and then they're usually organized by the mission. So we're going to call this out of the Themis namespace. And then usually the load routines are named after the instrument whose data you want to look at. And then we're going to specify, since Themis has 5 different probes in the constellation, we're going to specify probe A, and all these load routines are going to take a T-range argument. So we're going to set that to what we just defined. And then we'll print the list of variables that this routine returns, and then we'll plot one of them in PyTplot. So let's go ahead and run that. So you see it checked. It does go out and check the remote data server, and that's to check to see if you have that file downloaded already to your local cache. It does a check to see like the timestamp on the modification time on the server and the timestamp on the local file. And if your local file is out of date, it will reload it from the server. And you see it did find that we had that file currently already downloaded in our scratch space. And then here's the list of variables returned from that data type for Themis. And as you can see, we have quite a few different variables. We have a few different data types. FGS is what we call a spin-fit data type. So that's acquired every 3 seconds. Spacecraft does a complete spin. And so they do a fit over that spin interval. And so it just, think of it as a way of compression. We don't always need the full waveforms at like 8 Hertz resolution or 128 Hertz for the entire orbit. So that's the data type I'll be working with. And then you can see by the suffixes, we have a few different coordinate systems represented here. GSE is geocentric solar ecliptic. And then we have a similar one, GSM, which is referenced to the Earth's magnetic dipole. And we have DSL, which is a Themis-specific coordinate system that's sort of spacecraft coordinates. It's sort of with one axis oriented towards the sun. So most of our load routines will return a list of variables that were loaded. And then using Tplot, we could give it one of these variables or a list of variable names and call Tplot on it. And this is what we get. So this is so we have coverage through the whole 24-hour period, and that's maybe a little less than one Themis orbit. So you can see you don't see much out in the weaker parts of the field, but you can see as we go through perigee, we go through the much stronger parts of the Earth's magnetic field, and so that's what you have. So let's see. I mentioned the naming convention, parameters. Now notice we didn't really have to set anything on this plot. We have a sensible axis label over here, Themis AFGS. We have the units and coordinate system here. We have a nice little legend telling you what each of those components are. And how did Tplot know to do that? Well, that came out of the metadata that's stored in these Tplot variables. So that metadata is in the original data files that we downloaded, and it sort of came along when we loaded them into Tplot variables, and then Tplot knows where to look for them to set the defaults for the axis labels and ranges and so forth. So, so I've mentioned Tplot variables a few times. That's a key concept in PiSpeedAS and PyTplot. It's basically a container for timestamps, data arrays, and metadata. So with Tplot variables, at least in Python, we are always working with time series data. The data part of it can be just about like any sort of shape of an array, I believe will work there. So you have some data types that are just scalar quantities, some like the one we just plotted are vector quantities, and then we can even have more complicated like spectrograms or 3D particle distributions. So we'll take a closer look at what's in some of these Tplot variables. So this Tplot names utility tells you everything that's been loaded into Tplot variables so far. So far, we've only done the one load routine call, so you've seen this list up above. And now, to get access to the underlying timestamps or data arrays or the metadata, we use a routine called pytplot.getData. And then I'll also mention pytplot.timestring is useful for making the timestamps human readable. So as was mentioned yesterday, a lot of people want to use tools like this. The attitude is just, well, fill my arrays, and I'll do things my way from that point. So for you folks, I could probably stop the demo here and you'll be pretty happy, but I will go through the rest of it. So let's take this apart. So from PyTplot, we're going to import get data and time string. In this call, we'll get the FGS data from the get data call from this Tplot variable. And then in this form, get data returns a Python tuple. It has a field named times and a field named y for the data, and possibly additional fields that are relevant for spectrograms or higher dimensional data. So then we'll print the first few timestamps, we'll print the first few data values, and then we'll use the same get data call, but we'll set the flag metadata equals true, and then that'll give us a dictionary of all the metadata that's associated with that Tplot variable. And then we'll print some of the keys and print one of the dictionaries. So let's go ahead and run this. So here you see our timestamps that were returned after passing them through time string to get the usable readable versions. We have the first three data values here. So you can see that each value is a three-element vector. So that's your X, Y, and Z components of the magnetic field vector at that time. Then from the metadata, I printed the keys from that dictionary that got returned. So you can see that we have one sub-dictionary that's coming from the CDF. These data files are in CDF format. And every variable in a CDF has a bunch of metadata associated with it. And that's one of the main reasons we can do a system like this that can take data from such a wide variety of missions and pull it into a common environment. We have some metadata standards, some variable attributes that you are expected to provide with every data set. And as long as those standard attributes are there in data files, PiSpeedAS can probably make some sort of sense out of it. Let's see, so then we looked, last thing we did was look at the plot options dictionary. So these are nested dictionaries. And then we'll look at the y-axis options. And then you see, so we have a label there, and that's where that plot label came from. Some other things that are maybe not so relevant. We have a Y range here, and that it actually looked at the maximum and minimum Y values or data values in that array, so we know how to set the range for the plot. We have the axis subtitles, which have the units and the coordinate system, and the legend names are all in that metadata. Okay, so that's one load routine, and an example of Tplot variables. I just want to briefly show a read the docs page, which I believe is here. So this is a good starting point. We have a little bit of introductory information here, some of the installation requirements, and basically what I want to show you is the load routines we have available. So this is a list of all the various data types that are directly supported. And then if you go to them, let's say, let's look at ERG. So this is one mission, the Arase satellite, or it was originally called ERG. And here we have all the different data types that you can load from it. We have attitude data. We have a high energy particle instrument. And for all these, you can see that the parameter lists here are all very similar. So we try to make that as uniform as possible. And then for most of these, we have examples and example output plots. So if you're looking to see if a specific mission is directly supported in PiSpeedAS, this is the page you would go to. And if we support your instrument, we probably have some good examples there of how to load it. Okay. Let's see, we also have, there's the Python built-in help. And so that also, if you need a reminder of what the parameters look like for a given mission. Yes. Mike?
So under the load routines, I see Soho supported as well as Maven. Do you not support SDO? Or I guess just PiSpeedAS?
SDO, we do not, because we don't deal with a lot of image data. I think SDO, I'm sure they have other instruments, but most of the time I think you'd be interested in the imagery, and PiSpeedAS doesn't really deal with that.
Okay, thanks.
Okay. So I'm going to show another example. Yes. Oh.
So you recently showed the cell where you could get data to grab the metadata.
Yeah.
Are you able to change the metadata and then plot it with your changed metadata?
Yes. And hopefully I will get to that. We have there's a PyTplot.options takes a variable name and an option value.
Okay,
and,
which is changing the metadata.
Yes.
Yeah, okay.
Okay, so hopefully I'll have time to get to that. Okay, so we'll do another example, and this will be interesting because this is actually a spectrogram data type. So we'll see what happens there. So this is from the FEMIS ESA instrument. This is the electrostatic analyzer, so sort of lower energy electrons and ions. Again, just like before, we'll specify probe A and the T range we've defined. and we'll print the variables. And then we will print four, we'll print four, or we'll plot four of those variables. So go ahead and run that. Never mind those warnings. Our attribute structure is not quite squeaky clean for that data type. And you can see we got a lot of variables back from this one. So we printed four of them. This is, let's see, which one did we print? So we did electrons and ions from the FAST survey data resolution. And for each of those species, we did an energy flux spectrum. And then from the plasma moments, we'll look at the particle velocities for that species. So here it is. So we plotted 4 Tplot variables. So we got 4 panels and resulting plot. And again, the metadata defines whether that should be treated as a spectrogram plot or a line plot. So you can see that the energy spectra came through as spectrograms, and then the particle velocities came through as a vector data type, 3 trace line plots. And you can see there's some interesting stuff going on here. I'm not going to belabor that right now because we don't have time, but in a couple days, we will look at some of these type of plots and interpret them in a little more detail. I just wanted to show an example that generated a spectrogram plot here. Yes.
So if you go to the earlier plot, the Themis spectrograms, yeah. So this is great, but I definitely can't use this for like any sort of like publications or anything. So if I have to like fine tune this so that it becomes better, does Tplot have matplotlib like functionalities?
Yes, in fact, you can return the matplotlib objects and manipulate them directly.
Okay, so you'll be showing that today?
Maybe not. No, actually, I don't think I have any examples that demonstrate that. But if you look at the documentation for Tplot, you'll see there's a parameter called, I think, return matplotlib or return plot objects, something like that. And then you get the figure and the axes objects as return values. Okay, so I'm going to take one of these spectrogram variables apart and with get data and say a few words about that. So let's run this. So again, we're going to look at the timestamps, the times again, as before. So these are the data values. So each data point here is, how many is that? Is that a 30? Are we looking at 32? Yeah, so each data point has 32 spectral bins in it, or energy bins. And so you could see that in this tuple we got back, so you have this times component, you have the Y component, and now since this is a spectrogram, we get another component called V, and that gives you the values associated with each of those bins. So these are going to be in electron volts, I think, and these are the center points of each of those spectral bins. So those V values, those are what are getting plotted on the left-hand axis here. So we see for that date, we had 746 timestamps, and then the data values were 746 by 32, so 32 values per timestamp. And then the bin values also are 746 by 32. And that's kind of interesting because you might not think about this when you think of a spectrogram, but over time, especially for particle instruments, we like to run them in different modes. for, maybe more details for more interesting regions. But other times we might run fewer bins. So these bin values actually can change over time. And that makes it a little bit tricky sometimes to plot the spectrograms because, we have one mission where for each sample, the bin values are alternating. You have two sets of bins that go back and forth, and we have to figure out how to make a coherent plot out of that. And it was a little bit challenging. So the way spectrograms work, these data values are sort of, you think of those as like count rates or intensities, or intensity at that energy level in that energy bin, and then those values are encoded as colors in the spectrogram plot. So you can see a color map, color bar off to the right. So the redder ones are going to be the higher fluxes, and the cooler colors are going to be the lower fluxes. Okay, so look at a completely different data type. This is orbits for the Arase satellite. And so we've loaded and plotted that. And you can see this one, it's a little shorter orbit, looks like about an 8-hour orbit period on that. Interesting that for this one, the units for the distances are not kilometers, but they're Earth radii this time. So you can see that the plot scale and the subtitle here have changed according to that metadata. And then for this one, let's see, we'll look at the list of the orbit variables. So this one, they've included some additional information. They have a few extra coordinate systems here. Here they're representing the positions as latitude, longitude, and radius. Looks like they've also done some field line tracing. So they'll give you the positions and trace that field line down to the ionosphere and show where that trace ends, at the north end and the south end of that field line. So that's interesting. And you'll see that, sometimes you have to learn, do a little bit of research about what that mission provides in order for you to know what variables you really need to be looking at for that. So that's all I want to say about that. I want to show another data source here, OmniWeb solar wind parameters. We'll be using those a bit later. So we'll run those. There's just one load routine data, and it returns all the OmniWeb data. And so for this one, we're going to plot the proton density, the flow speed, and the pressure for the time range of interest. And here are the plots we get. So you can see a lot of variations. So this was, especially the early part of the day, there's a lot of activity. And you can see by the solar wind flow pressure. And later in the week, we'll talk more about how that impacts the Earth's magnetosphere. This is also, this data set's useful if you want to do magnetic field modeling. Because of course, the shape of the Earth's magnetic field varies depending on the solar wind parameters. Let's see, we'll also look at some ground magnetometer data that I mentioned at the top of this presentation. Let's see. So in this case, these are all accessed through the Themis mission, through the GMAG ground magnetometer instrument type. But I think most of the other magnetometer networks have had their sites added to this routine. So this is probably where you would go for any of the ground magnetometer data. So here we're going to load data from 3 sites, Fort Smith, Fort Yukon, and Athabasca for the time range of interest. So you see here with ground data, the nomenclature is a little different. We call that parameter sites instead of probes. And here's what we get back. Now the ambient field is so strong here, you can't really see any details. So I'm going to use one of the PyTplot sort of mathy routines. And what we're going to do is subtract the median off of one of these and then just see the variations that are left over after you take the ambient field out. So we'll do that. And there we see a much more interesting plot. We're seeing just the variations after subtracting the median. And now you can see, again, early part of the day, a lot of activity even in the ground magnetometer data. Okay, so that's it for this particular notebook. I'm going to try to come back to my slides now. Let's see. Bear with me for a moment here. Let's see what, where am I? Oh, okay, I've completely lost my pointer here. Oh, okay. Somehow I got back. Okay, so just want to recap what we've covered so far. Tplot variables are the main data structure here. They're a container for timestamps, data, and metadata. I don't think I mentioned this earlier, but internally, times are represented as Python datetime or NumPy datetime objects. When you get them back, yes? I'm not there. Sorry. Yeah, I can't find my pointer to get to that little control. Thank you. Okay. Yeah, times represented internally as datetime or NumPy datetime objects. That choice was made, I believe, because that's what matplotlib likes on a time axis. When you call get data, by default, you get back a floating point, basically Unix times seconds since 1970. There is an option in get data if you just want to grab the datetime objects themselves and work with them. Data values can be scalars or multidimensional arrays. We have a metadata dictionary. We didn't demonstrate this, but store data is the inverse of get data. You pass it in a name for the new variable, and then a dictionary with an X value for the times, Y value for the data values. You could pass in the attribute dictionary, and then you could create a new Tplot variable that way. Yeah, as I mentioned. So we've covered a few different load routine examples. So generally, the load routine parameters, they're going to take a time range, sometimes a probe if it's a multi-satellite mission, an instrument type, and often some data type parameters in case there are multiple data types provided. Behind the scenes, what PiSpeedAS does is usually it'll use those parameters, create a list of URLs to check for whatever data provider they're coming from. And then it'll contact the data server, do the thing where it checks for the local file, checks timestamps on the remote file, and then to decide if it needs to download a new copy of that file or not. Downloads them if necessary, and then uses the appropriate. Let's see, what did I do there? There we go. And then we have file format readers for CDFs, net CDFs. There's one other one called STS. I'm not sure where that's from. Somewhere in there, I'm sure there's a FITS reader. So PiSpeedAS can handle any of those file formats and load them into Tplot variables. PyTplot.tplot takes a list of Tplot variables, generates a matplotlib plot with each variable on its own panel as a line plot or a spectrogram, and that's controlled by the metadata. PyTplot.options, as I mentioned, takes a list of tplot variables, an option string, and an option value, and it sets that option for that set of variables. So that's how you set line styles, colors, axis titles and subtitles, plotting limits, and so forth. You could plot the most line plots or spectrogram using the spec option. And as I said, most of those options are already set by the load routines, but if you want to tweak the appearance of the plots, that's how you do it. And then we have another one called let's see. All right. Sorry. Yeah, Tplot options set some more global options that are not specific to just one panel or one variable. So with that, you could change the main plot title at the top of the page size, separation between the panels, and the time range to be plotted for all the subplots. Let's see. So I already mentioned sort of what goes into a line plot or spectrogram plot. We have a few other plots available. Orbit plots, where you take like a 3D orbital positions and project those onto a 2D plane. Or we could also take 3D particle distributions. So the three dimensions you're working with here are sort of azimuth versus elevation. And then for each one of those angular bins, you usually get a list of energies. And so you can take that three-dimensional structure and take a 2D slice through it with respect to various coordinate system axes, and then see how the energies or velocities project onto that plane. And that's a useful way of looking at particle data. Now those last two, those are not directly implemented by Tplot. Those are things where you'd have to just go straight to matplotlib and construct the plots that way. Let's see. Any questions before I go to the next notebook? Yes. Mike.
Thank you. From the TMIS electrostatical analyzer data, do you have any form of the code or the model that can analyze the velocity distribution function of those H particles?
Yes. You're asking how did about the particle velocity?
Yeah, I'm talking about the velocity distribution function of.
Yeah, those actually came. Those were pre-processed by the Themis Science Operations Center and put into that CDF file. So PiSpeedAS didn't have to do any analysis on that, but we do have tools for working with the 3D particle distributions, and then you can use those to calculate like the velocity moments or densities or so forth. And we can't really do that yet for Themis because that PiSpeedAS routine requires calibrated 3D particle distributions. And we don't have the Themis calibration code ported to PiSpeedAS yet. But we do have that full functionality available for, I think, for MMS and Arase, maybe even Cluster. I'm not sure. But yeah, so usually you have the option of getting those particle moments and sort of derived quantities either directly from the data files published by the data provider, or if you have access to the full particle distribution data, PiSpeedAS can do that if you have the calibrated information. Does that answer your question? Okay, good. Yes, back here.
I'm just curious if you'd already downloaded the data as CDFs, and then you wanted to use PiSpeedAS to pull them, to access them and make them Tplot variables. How would you do that? Because I think we only went directly from downloading straight to as Tplot variables.
Oh, no, well, you just didn't see much of the step where it goes to the file first, and then we read the file. If you know that data is cached, you could just call the load routine again with the
Oh, and it will
time range.
say you already have it.
Yeah, or we in PyTplot, the file format readers. So if you have a CDF file and you want to load it, just load that one file without even going through the load routine. You would call pytplot.cdf_to_tplot, and that'll load that file as tplot variables.
Great. That's wonderful.
Yeah, but what you miss sometimes with that method is sometimes the load routines can do a little bit of cleanup or tweaking of options and so forth. So with the method you're talking about, you only get what's actually in the CDF.
Gotcha. Thank you.
Okay. Okay. Let me try to navigate to another notebook now. And let's see. There we go. So I'm going to go ahead and close this one. And I'm going to open, this is PyTplot variable options. Yeah, here we go. Okay, so I'll run through this probably a little faster. I just want to sort of demonstrate a few of the options that are available for you. So again, we're in a fresh notebook. So I'm going to set the environment again to our location of the data cache. We'll do our fresh imports again. And this time, I'm going to import Tplot. I'm going to import the options command and tlimit command. I'm not sure if I actually use that in this notebook, but there it is. So we've done our imports. Again, we have to load some data to work with. So this time I'm going to load Themis state data. That is a data type that holds our orbit and attitude information. So here I'm going to specify the time range directly. This is the same time range we're working for. And again, we'll use probe A. So there we are. And there's a lot of data returned. What we're interested here are going to be the Themis positions and velocities in GSE coordinates. So we'll go ahead and plot those. And here are two orbit plots. So you can see sort of to the right here is the perigee. So that's when the positions are smallest. Out here at apogee, we're like 75,000 or so kilometers out, at least on the x-axis. And then you can see with the velocities, as we go through perigee, the velocities are bigger, and then they decrease as we go towards apogee. Now, let's change a few things about these plots. Let's try changing the colors for the velocity plot to all black. PyTplot, we're using the matplotlib version of it. Matplot lets us use these single letter color codes. So K is black. So we'll call the options command. We'll give it the variable we want to change. The option is color. And then the option value, we have 3 traces on that plot. So we'll give a 3-element array, black, black, black. So we'll set that option and plot the panel. And there you see that bottom panel. We've turned all those traces to black. Now, if we want to set it back to blue, green, and red, matplotlib also recognizes sort of the more usual color names. So this time we'll set them back to blue, green, and red. So again, that's the options color option. And there we are. We're back to what we started with. Now, if you're like me and you can't remember which way the axes point, you always find yourself doing the right-hand rule. Maybe you want that right on your plot. I don't know, you probably wouldn't publish this, but let's set the legend names now. Instead of X, Y, and Z, we'll call them index, middle, and thumb. Oops. And there we go. And you see, I actually passed a list of variables here. We had defined that panels variable up above with both the position and the velocity variable. So you can use options to change a batch of variable options in one call. So that was the legend names option and the legend values. And here you can see in our legend, they have been updated. You can change the line style. So that's like whether you dotted or dashed or dot dash or what have you. So go ahead and run that. We'll change the positions to dotted and the velocities to dashed. And this is probably pretty hard to see unless you have microscope eyes. But the legends can help. You can see legends up here. These are solid lines. So you have like longer bars here in the legends. For the dotted one, you could see that the dotted lines show up in the legends. And then you can see that these dashes here are a little bit shorter than the solid bars up here in the legend. So that call did do what we wanted. Okay. Then the T-limit routine, and this is more of a global option, I think. I think that would affect all the panels. Yeah. So you could give a time limit, a start and stop time that you want to zoom into. So we'll go into just this 12 to 1500 hours and plot it. And there's our plots. You can see previously we had the whole day. And now we've zoomed in to this region, 12 to 15 hours UTC. And then if you want to go back to the full-time range, you can set the Boolean option full to true and then replot. And now we are back to the full-time range. So that's useful if you're sort of exploring a plot. You want to look at a little time range, but it's good to know that you can always get back to that full-time range if you need it. You can also set the axis ranges with the options routine. So we're going to load a different data set that has a little more interesting structure to it. We're going to go back to our plot of FGM data. Let's see. There we go. And there's our plot. So you can see sort of the large field values near perigee have washed everything else out. It's hard to see any detail. So one way you can alleviate that, well, you could zoom in on a shorter time interval if you know where to look. But if you don't know where to look, you might want to try reducing the Y range. So here, so we can see we're going up almost to 20,000 nanoteslas. Let's cut that down to plus or minus 200 nanotesla. So that's the Y range option. And we'll go ahead and run that. And now you can see we've zoomed in on that Y range. And now that we don't have those giant values in perigee washing us out, you can see that there's actually some very interesting variation. Again, the early part of the day when things were active. And so there is interesting data there. Okay. Any questions about options? Yeah, I think I'll just leave it at that. Let's see. Now let's see if I can get back to my presentation. I don't know why you can see that, and I think I don't know. I think I have cursor blindness or something. Okay, let's see. Okay, so I think that's pretty much all I want to say about the plotting options at this point. I do want to talk a little bit about analysis tools. So PiSpeedAS and Tplot have, as you might expect, quite a variety of tools that you can operate on Tplot variables with. So some of them are simple arithmetic. So if you want to take Tplot variables and add them, subtract them, multiply or divide them, we have those routines, and they're called add, subtract, multiply, and divide. We saw an example already where you can subtract the median from a Tplot variable, and that can have very useful results. We have several different coordinate transforms that you can apply. The ones that are, let's see, GEI, GSE, GSM are sort of the main ones that get used a lot. And then there are some routines in PyTplot to do more complicated things like field-aligned coordinates, where you're taking the local magnetic field direction and then referencing the coordinate system to that. And then we also have some mission-specific coordinate systems, like for Themis, where you have some quantities are given in more spacecraft specific coordinates. And so usually that mission will supply some way to get from those spacecraft specific coordinates to a more widely recognized geophysical coordinates. Interpolation is another thing that you have to do a lot. So you can interpolate between between raw data arrays, or interpolate one Tplot variable onto the timestamps of another Tplot variable. And then we have several different routines, and with all kind of slight differences in terms of what sort of data they operate on. We have one that's specifically, like if you want to ignore NANDs in your interpolation, sometimes that's needed. If you want to make sure you don't have any of those NANDs in your interpolated data. Let's see, we have some tools for doing wave polarization analysis on fields data. And also along the same lines, you can generate power spectra or wavelet analysis. We have one that I'll demonstrate in a couple of days about magnetic null finding. If you have, like, there are a couple of missions, Cluster and MMS, that fly their spacecraft in tetrahedral formations in fairly close formation. And if you have those observations at those 4 points, you can actually locate magnetic nulls, which are important for reconnection. So I'll demonstrate that a little later. And then we can also do magnetic field modeling using the GeoPack external package. I believe that's also a PyHC package. And that's an implementation of if you've heard of the Signanenko field models, so like T89, T96, T01. Those originally came from some Fortran code that was ported. There's an IDL interface to it. And then someone has ported that Fortran code to pure Python code in the GeoPack module, or the GeoPack package. So the magnetic field modeling is what I would like to demonstrate next. So that is the magnetic field modeling notebook. So I'll close this one, open this one. Okay, so this is going to explore the PiSpeedAS interface to the GeoPack package. So we'll set our environment variable again to use the previously cached data. So as usual, we'll import PiSpeedAS, PyTplot, Tplot, and now from PySpeedAS.geopack, we'll import the T89 routine. And that's our wrapper around the T89 field model. So there's a few ways you could use these. So one method of doing the field modeling is you sort of define a grid of points in three-dimensional space, and you generate the field at all those points for a given time step and see what the field looks like globally. What we're going to do is more like a fly through. So we're going to take some Themis satellite positions and times, and then we're going to generate the model field for those times at just those spacecraft positions. And then that'll let us do a comparison between the Themis data and the model data. So first thing we need to do is get the orbit. So we'll use that again. We'll load that with Themis state. For this, we're going to use a different time range for this. Let's see, because I don't want to spoil anything that's coming up later. So here's our probe position for that day. You notice we used GSM coordinates. The GeoPack library pretty much works in GSM coordinates. This one, T89 model is very simple. It only takes one parameter, and we're just going to take the default for it. It's basically the KP, the planetary K index. So here we've plotted, this is our original spacecraft positions. Here is the field value that was returned from the model. You can also get the IGRF model out of the GeoPack library. In this case, we do that through the TT89 call, and that one takes an option IGRF only. So the way these work internally, it generates the IGRF model and then adds some perturbations to it based on which model you're using and what model parameters. So we'll get the IGRF only from this call, plot it. And then we can see what those perturbations were by subtracting off the IGRF only field from the T89 field. And then you can see that that the T89 model differs by a few tens of nanoteslas from the standard IGRF model. So that's kind of interesting. Here we can we'll actually explicitly pass the parameter value to T89. So we'll use this IOPT is what it's called in the Fortran world. It's one more than the KP value. And then we'll generate that, and we'll add a different suffix to this output just so we don't clobber the original one that we generated. So this would be what the model looks like for a more active field. And there you have it. Oh yeah, so in this cell, we've actually subtracted off the original model. And so you could see that the activity index we passed in makes a difference of about 100 nanotesla in the model outputs. So now we'll look at a little more complicated model. This is the Sigonenko T96 model. It takes more input parameters, and we're going to have to load those using the Omni data set and also the Kyoto DST index. So we're going to define a little helper routine to do that. And I'm not going to get too far into it. Basically, we load the DST data from Kyoto. We load the other data sets from Omni. This is, we take 3 of these parameters that were returned from Omni. We're going to make them into a single vector. And this get TSY params is going to pack everything in the right data structure we need for the T96 model. So we'll go ahead and make sure that routine gets defined. So here you can see we've loaded the model parameters we need, and it put that in a Tplot variable called T96par. And now we can generate the model data. First thing we have to do, it's very important to interpolate those model parameters onto the timestamps that you are using for the positions. So we'll do that interpolation step, and we'll pass the interpolated parameters to TT96. So you can see here's the original parameter set that we started with. And then after the interpolation, you see it's been cut down to just that 24-hour period. You can't really see it here, but it's exactly the same timestamps as the input positions. And then here is our T96 field model output. And now we should look at the difference between, well, here we're going to look at the difference between the T89 model and the T96 model. So again, we'll use PyTplot to dot subtract on those two variables. And here you see the differences. Now, before we looked at the difference of two models, it was all very nice and smooth. And that's because we were using the same model parameters for the whole day. In this case, we're using real data from OmniWeb and from Kyoto DST. As you can see, this is a little more realistic. Everything's a little more jagged as the conditions are changing during the time period. And I think I'm going to stop there. I have 1 minute left, I think. So, all right. So questions about field modeling or any other general PiSpeedAS stuff? Yes.
Thank you for going over this. I do a lot of sync and enco work at work. I was wondering, I use a lot of this package to generate the magnetic field for geostationary satellites. Specifically, my question refers to the Sync and Enco 04 model, where you can use Omni data as input. Can you use other solar wind input data? Like, can you change?
Yes.
Okay.
Yeah, it doesn't really care where it comes from. For example, sometime, time here. Like, for example, you might not want to use the L1 solar wind monitors because those field line, they might not necessarily connect to the Earth. So sometimes if like one of the Themis Bravo or Themis Charlie or the Artemis probes, they're in lunar orbit, they spend a lot of time in the solar wind. So if they're in a favorable position, you could, in theory, use Themis data as your solar wind monitors, or if you have it from Discover, or I think I don't know if some of the geostationary maybe you could even use the in situ like proton speeds or proton. I don't know if you have those measurements.
I was working on code to propagate Discover to the bow shock for the solar wind input data, but because Discover is kind of old, the Faraday cup isn't working so well, so we can't really get fantastic looking data. So we're just wondering for the future, like when we don't have Omni anymore. But yeah, that's good to know. Thank you so much.
Okay. Anyone else? All right. Thank you so much.
Thanks, Jim. All right, to keep on time, we're just gonna have a slightly shorter break. We'll come back at 10:45.
Thank you. Thank you very much.
Actually, I work on one theory, theoretical plasma physics. So I do more of a simulation and what's it called? Dispersion relation of nonlinear wave, and plot the electric field and estimate the electric field. To estimate the electric field. So
All right, let's go ahead and get started again. We're now moving on to SpacePy, which is going to be presented by John Niehoff. Also, is this anyone's phone? Okay, I'm just gonna like set it in this general area. Go ahead.
All right, so the obligatory can you hear me online question? If somebody can just look at Google chat and make sure that the answer is yes. Okay, thanks. Okay, Darren, just.
That's perfect.
Okay. Sean, can you still hear me online? All right, thanks. All right, so I'm going to be talking about SpacePy. I'm going to focus really on the interactive notebooks and just kind of blow through the intro material here, just to set a little bit of scale. So we've really always envisioned SpacePy as being one of the tools in the toolbox. We're really trying to be part of the big scientific ecosystem. I don't think I need to introduce NumPy, SciPy, or Matplotlib to people anymore. But what we have is the domain-specific space science functionality that complements those general tools and then interacting with them. We're really focusing a lot on this interoperability piece going out to and from AstroPy and Pandas in particular. So this is just a increasingly out-of-date diagram of kind of the ecosystem. There's a pretty wide range of applications ranging from plot visualization tools through various conversions of time and coordinates, which Bob will talk more about later, and with a pretty wide range of level of the interface. So from fairly high level stuff like SpinVis, like SpeedAS and PiSpeedAS, which are meant to be pretty high level, down to some low level stuff like Urbim and Leyland Geomag. SpacePy is really kind of in the middle. It's meant to be a library more so than like an integrated environment, and something that you can use to piece together what you need to do for your analysis, or as a component used by higher level toolkits. So get an idea of our scope. We are open source. We're under the PSF license because when we were dealing with lawyers, that seemed like a really good idea 13 years ago. As it turns out, I has moved on to the BSD license, but it's still fully BSD and GPL compatible. It's just phrased a little differently. And do not mess with relicensing at a nuclear weapons lab. It's just not good. As I mentioned, it's mid-level. The domains we work in are pretty much from kind of MI coupling out through the inner heliosphere that mostly reflects the research interests of the developers. And the development is always very need-driven. It's driven either by a research project or a mission need. But that's need-driven, that doesn't necessarily just mean the needs of the developers. If you're working on something and need something that fits well within this paradigm, please come to us, open an issue, we'll talk. One of the key points here is the data model. It's fairly lightweight. It's very similar to CDF or HDF5. Basically, it breaks down into dictionary-like things and array-like things. And both of them have metadata attached to them. We don't force any particular metadata standard. The interpretation of the metadata isn't really enforced by these objects, but we're moving more and more towards assuming the ISTPS PDF metadata so that we can actually perform operations on there. Give you an idea of where we're coming from file type wise. All of these come into the data model representation. So that's HDF5 in and out, NASA CDF. I'll show you some of this JSON headed ASCII. And we also have conversions to and from the Pandas data frame. We have documentation. It's Sphinx. This is all pretty much what you expect these days. Couple of models that we have. We have the Urbim library included. So that's a lot of magnetic field models, field line tracing, shell tracing. We have support for the AE9, AP9 model output, some empirical models for the plasma pause, L-star, and then Urbim has a whole bunch of stuff that comes in terms of external field models. And just a few of the tools we have superposed epoch analysis, bootstrapping of confidence intervals, the time of coordinate conversions, CDF library, All of that Fortran urban library stuff is exposed. Some various plot helper routines I'll show you a little bit, and output analysis and visualization from the space weather modeling framework, which we'll get into more. So I want to jump ahead to the notebooks here. So all this is preloaded on the Helio Cloud, just like everything else. The Helio Cloud notebooks are set up to run in Helio Cloud. They do have very specific instructions for if you pull them off of Helio Cloud, how to run with them. We also have a separate repository where those changes have already been made. So you can pull from that if you want to do this offline later. All of the data is preloaded onto Helio Cloud, but we also have all of the data for these are available elsewhere. A lot of it's in existing public repositories. There's a few cases where we have sort of intermediate products that were designed for specific paper, and those we have uploaded in Zenodo. So all these are in Markdown, so you can actually look at them directly, but you do need to be careful that you open them as a live notebook if you want to execute stuff. I'll show you that. There's 4 notebooks in there. We don't have time to go through all of those today. I'll be going through 2 of them. You can feel free, if you have nothing better to do at lunch, to go through some of the other ones on Helio Cloud, or when you get home, go and grab them from our examples repository. So in that case, please either corner me if you have questions, or you can ask in the Slack. We'll be following that. So it's just, we find the best way to show how this stuff works is with these examples. Most of these are based on particular studies that we've done. So definitely encourage you to tear into that. All right, so as I mentioned, just be sure when you open, if you're in Jupyter Lab, you do a right click and open with Notebook specifically. So with that whirlwind, I'd like to go and dig in. So if folks want to open up, I think it's probably a little bit easier to see if you have this up on your screen, but we're going to start with this cutoff rigidities notebook. And you can right click or Mac equivalent, open as notebook. Shrink this over. Can I dismiss this remotely? Does this matter? Okay. Fortunately, I have anybody's email coming up. All right. So folks who want to follow along, have this ready. So this is courtesy of Steve Morley, and Steve was joking with me this morning that nobody's ever learned anything from him. So we'll see if it works any better with having another person present. So the upshot of this is to demonstrate the direct access of high energy ions into the inner magnetosphere, or the lack thereof. Because, of course, of the magnetosphere, any incoming solar energetic particles get that nice V cross B force, and up to a certain energy, they wind up getting slung basically right back out. And that's a very qualitative way, and this is a notebook digging into doing that more quantitatively, using SpacePy, but also using a lot of other parts of the ecosystem. All right. So we have everything set up, as I said, in Helio Cloud, and so we just have this cell here. If you're following along, be sure to run each cell as you go, because if you skip ahead on cells, that's often using a later cell will use variables referred to earlier, maybe part of the problem. So this is the simple thing, and this one's very simple. If you run this at home, just change this true to a false. That's it. And then this is doing some setups to make sure that we're using a shared set of the Omni data and other information. And this is just a whole bunch of imports, which you can take on faith at this point, and we'll describe that. All right. So one of the key pieces of data we're going to be looking at is the energetic charge particle data from GPS, which is not a data set people see a lot. It's very interesting for this purpose. We've already downloaded it, but we're still going to run this cell because that just specifies the set of satellites we're going to be looking at and what the file names are for that downloaded data, so we can loop over that easily. All right. So particular relevance here is we're just sort of defining a string here that has one left out parameter that we'll fill in, which is the satellite number. So the first thing we'll do is just read in one of those GPS files into the SpacePy data model. So that's a one-shot read. This format is the nice ASCII comma separated variable that some folks really like to deal with, but it has glued to the top of it a bunch of metadata in JSON. So the idea is this is a file format that can both play in the I just want to throw it at Excel crowd and I want this to be self-describing. So this is supported by SpacePy. It's also used by Tplot and a number of other systems. So we can take a look at the data and the metadata that was read in. So this dumps out that dictionary-like object with our keys, some information on the type and the size. And then for those that have more detailed metadata, so for instance, the latitude gives you an idea of what all that is. And scroll, scroll, scroll. Okay. So Bob's going to go into a little bit more detail on the time. The interesting thing about this is that the GPS data is not surprisingly in GPS time, which is they decided to come up with their own time base. And that is a continuous time base. It doesn't deal with leap seconds. When you have those continuous time bases, so GPS is one, TAI is another really common one, they can be presented in one of two ways. Sometimes they're presented as just a count of seconds since an epoch. Sometimes they're presented as like a year and a day, whether it be a day of year or a month and day. That's fairly common for astronomers using TAI. So just be aware if you have something that looks like a date, it's not necessarily a UTC date. For the most part, my general rules on time are, if you don't need absolute precision down to a couple of seconds, you don't have to worry about much of anything. If you have to worry about absolute precision down to a second, you're probably okay. If you have to worry about absolute precision to better than a second before 1972, come and find me, buy yourself 3 beers and me 1 beer, and we'll talk. But the upshot is that the GPS particle data is in GPS time, and we're going to go in and just try a very naive day of year to date, because this is a year and it has a decimal day. I'm just going to go and set that up. All right. So that has our first time as being nominally 4 minutes into that day. But we do know that that this is actually in GPS time, so we're going to be a little bit fancier about it. All right, and we're going to start with moving it to a nominal date, pulling off what we know is the 0 epoch for GPS, and then converting back to total seconds. And then you kind of have your choice of approach. You can use SpacePy TikTok or AstroPy time, and Bob will get into this more this afternoon, so I'm going to kind of skip over that. All right. So that's dumping it out with an internal, and there we go. And you can get fancy on exactly how much detail you want here. So it's 339, our previous is 355. So that's our 6-second leap second difference. All right. And there's our AstroPy time. And let's see here. I think when we first passed this into AstroPy, we were not specifying the right offset. But you go onto the deals on this. The upshot here, we're just going to keep this here so we get the time in there, is that you can pretty easily pop back and forth between the SpacePy time representation and AstroPy time. You can create a SpacePy time object by passing in AstroPy time. You can do the .apt to get it out, so you can bounce back and forth as you like. Yeah, please.
I guess I missed it if you mentioned it. What's
Yeah.
the difference between AstroPy time and SpacePy time, and why are we converting it?
They're just two different approaches to dealing with times. The upshot being that AstroPy didn't exist when we started writing SpacePy. And the support for certain time systems is different. It's handled differently. But the upshot is really you can take whatever approach you want. There are things within SpacePy that assume you're passing in the SpacePy time object. And if you're coming in with an AstroPy time, you can just do the convert over. So it has to do, I think, as with a lot of things, what is expected by the teams that you need to do to get your job done, and what exposes an interface that works well with the way you think. Right. And that's why we focus on the interoperability, is that you can make that choice freely. But yeah, thanks. That's all right. So let's take a look at some of the Proton data. So this is just some nice basic matplotlib stuff where we're passing in the time, we're passing in the Proton flux, and then we're doing some smart time ticks on there. So hey, this is great. We're getting Proton flux integral. This is above 30 MeV going over time. Anybody know what this periodicity is? So this is just the periodicity of the actual GPS orbit, because it's an inclined orbit. What's happening is we're basically sampling different L shells at different points in the orbit. So as we're going through places where we're essentially in the loss cone of the radiation belts, we're picking up more. So this is how you can have a circular orbit that probes multiple L shells. All right, and this is a time series. If we want to just convert this over and view it as a function of L shell, as I was mentioned, the L is actually included in the big space data object that we read in from that file. And the SpacePy spectrogram object will go and rebin that for you. So we can pass in just a set of time. We pass in a set of L values as a function of time, and the actual flux data also as a function of time, and then get that out as a nice spectrogram. So here we are getting the flux as a function of the L shell as we go around the orbit, and as time. So you can see that we obviously don't have total coverage, since this is only one spacecraft in the orbit, and it's going and picking the bin sizes for us based on the input. But you can still see a couple of key features of this time period. You can see that initially we have fairly low fluxes. We have an increase as a solar inject particle event arrives. And you can see that it eventually, the L shell at which we have kind of any counts at all starts to move inward as the event progresses. And we'll look at that in more detail. And then we have a substantial population in the inner L shells that goes on for some time afterwards. All right. This is quite possibly some trapped solar inject particles. It is also entirely possibly relativistic corruption, and we'll leave it there to check. And to give a little bit more context, we can look at what's going on in terms of geomagnetic activity using the Omni database. So the Omni database in SpacePy is derived from the Kendenton parameters, which are derived from the Omni web data. And this is stored as a local copy that's been processed into a database, and then it goes and does the interpolation for you. So all we're specifying here is a time period we're interested in. We're making that as a SpacePy time object, which is what's expected by the Omni module. And then we're asking to get that data out. And then we're doing a nice traffic light level plot of that KP variable against a time with various colors. So see here that SEP event is starting in mid-2022 and mid-22nd of June. And that's also about the time that KP kicks off. So what we're having is a very geomagnetically active period that is following the arrival of the SEP as the associated shock comes on by. All right. So given this information, what we'd like to do is fill this in a little bit more, get some idea of the global picture by using the multiple GPS satellites and seeing what effect this KP, this heightened convection, has on where things penetrate from the SEP event. So again, we're just making up a set of start and stop times that really covers that period late on the 22nd. And we're going for a 90-minute period. It's expressed as a fraction of a day. And then we're doing some ragged L-shell bends that are finer at the inner Ls. That works just fine. And then we're defining the spectrogram object. So this is just setting up what we expect the output of that spectrogram to be. And then we can go through and load in the data by reading one satellite data at a time, converting from GPS, and then loading the time. In this case, we are doing explicit date to num. The reason for this was because when we first wrote this up, there was actually a weirdness with the new versions of Matplotlib. I'm leaving this in because it illustrates an important point. Matplotlib does a pretty good job if you hand in like a bunch of date times. But if you're doing stuff with P colors and mesh objects and something more than a time series, sometimes it gets confused. And if you're not getting out what you expect to get from Matplotlib, you can always just try casting those explicitly and see if it's happier about it. So it's just a trick to get in there. So we're going ahead explicitly casting that and then adding in our Proton Flux as well. And we're not trying to do this in any particularly organized fashion. We're just taking a bunch of time series from one spacecraft, a bunch of time series to the next spacecraft, concatenating it all in at one go. And then the spectrogram object itself will take care of binning that and lining the times up. All right. So again, we're doing some nice Matplotlib stuff. We just want a 1 by 1. And then we're plotting the spectrogram. We're explicitly specifying the target. That's not always necessary, but this is a pretty common feature of the SpacePy plotters that you can just say, plot this, it'll make something new, or you can say, hey, I have this whole figure, please put it in this spot. Put it all together. All right. So this nicely fills in our coverage because we're pulling from multiple spacecraft now. This is kind of the most intense part of the SEP event, but what's really interesting here is if you look at the lower bound of where you're seeing substantial flux, that's creeping inward to those inner L shells. And remember, when we were looking at KP, this is the periods where KP are enhanced. So as we're getting the enhanced convection, the enhanced ring current, that's effectively weakening the external geomagnetic field such that you can get closer in penetration of the SEPs. All right. Are there questions at this point? It's a good point to pause. Sean, is anything online? Okay. So lots of references if you're more interested in this. So we can get a little bit more quantitative about this. There is a minimum rigidity or energy that can penetrate into the magnetic field based on the angle at which you're coming into the field and what field you're on. So yeah, I'll slide it down here. So the Shields PTM code, this is open source. That's available. I'm not going to get into it, but that's one thing that's useful to look at if you're interested in this thing. By the way, why are we doing this as a dipole field? Anybody have thoughts on that? So we're close enough in that we can cheat, right? We're kind of looking at L shells of 6 are in, so we can kind of cheat, declare it dipole and kind of work from there. All right. All right. Anybody want to guess what the magnetic dipole moment of the Earth is expressed in units of nanotesla cubic Earth radii? Nick's like, why are you using units like that? And the answer is because if you think of the magnetic moment of the Earth's dipole in terms of nanotesla times cubic Earth radii, that's just the field at the surface of the Earth. So not surprising, that's about expect. Okay, so this is just a little function that is set up to go from those hideous units into CGS, which is basically what sets for it. And this is expressed in terms of a vertically incident particle, which if you run through the math and Sturm basically winds up being a 1/4. So that's kind of a reference rigidity. So we'll run that. All right. And as we said, we're treating this as a dipole because we can cheat in that way, but even the dipole does change a bit with time. And so we can look at that impact on the actual shielding effectiveness of the magnetosphere. And we're pulling in the particle class from Shield's PTM, not to Displasma Pi, which has got something very similar, but as an illustration of putting together an abstract class and doing things with it. So I'm going to skip over kind of that software engineering bit of it. But you can look back at this. And Nick, I promise we will actually do this with Plasma Pi as well, so people can see both approaches. All right. So we're defining an abstract class for a particle. We're going to put together a proton as a very nice simple thing. And we don't even need to look stuff up. We're just going to use the SciPy constants to do that. All right, so now we've got a proton and we can kind of get out its rigidity and the corresponding energy here, right? So we'll skip that. All right. In SpacePy, we do have a instance of the IGRF, internal field model. So we can work that. That pulls together from a number of different references to get a good time coverage. Again, we're doing a tick range here. We have 90-day increments. So we've got about 500 steps here over the last 100 odd years. And we'll just go and calculate the moment for each of those times. Put that in there. Defining a quick little function to find that cutoff rigidity. That's the rigidity that can't penetrate any further than a particular L. So that is run. And let's actually take a look at that. All right. Skip most of this, just so you can see the output here. So what we've done here is we've calculated what the cutoff rigidity is for a vertically incident particle on the surface of the Earth as a function of time based on the IGRF model. So here's the cutoff rigidity, here's the proton energy. All of this stuff is basic Matplotlib stuff, which you can dig into those details. And then there are kind of rules of thumb that are used that kind of, if you back it out, it kind of corresponds to what the value was in 32 and what the value was in 88. You'll see this here. You've seen this in a lot of other ones where there's this big splat of like 20 lines of Matplotlib stuff to tweak it. This is a case where the notebook approach is kind of difficult if you're trying to like work this out interactively. In practice, you're going to be sitting like an IPython window, going to bring something up, and you'll start iteratively working on, okay, what do I need to tweak here? What do I need to tweak there? And then ultimately capture that in a script or a notebook for communication purposes. But I guarantee you, none of us sat down here and wrote this out of our head from the get-go. I know exactly what set of Matplotlib calls I need to do to make this work. All right, you kind of build this up piecemeal as you look at it. All right. So given that, let's then also look at that actual vertical cutoff rigidity as a function of time and energy, right? So over time, cutoff rigidity of a vertically incident particle at various L shells, right? So you can see that we're getting penetrating particles at basically lower energies as we go on in time, and the IGRF field is weakening, and there's the Proton energy there. And there's one last example on dumping stuff out, but I want to move on to the next one because it has like the cool looking figures on it. Any questions on this? It's a lot of stuff together. And if any of this looks interesting, I encourage you to take a look at the notebook after the fact. Cool. Let's look at some MHD code output. So pull that one up. So that's the SWMF dynamics one. Again, we open it with a notebook. And I think Dan Welling's online. So Sean, if you can just keep an eye on Dan Welling suddenly starts screaming in the chat that I'm telling something terribly wrong. Sorry, happens already? Okay, not yet, good. So the space weather modeling framework is a set of coupled physical codes for pretty much sun to mud modeling. And these are big codes, massively parallel, tend to run on pretty big computers, which of course going to be moving to the cloud. But the output we can visualize on much tamer machines in a nice interactive way in Python. And so that's what the PyBats module of SpacePy is meant to do. It's named PyBats after Bats Are Us, which is the global magnetic spheric MHD model component of the SWMF. As I said, mostly it's kind of oriented towards supercomputer right now. There's definitely some conversations on trying to make SWMF and its outputs much more cloud enabled, so that you wouldn't be downloading the data off of the supercomputer onto your local system. But that's kind of the mode we're working, the mode we're going to demonstrate right now. All right. So the data for this tutorial is on Zenodo. It is based on a paper that Dan published a few years ago, which is basically a maximally, not maximally geoeffect, but a maximal solar event. So the modeled event starts with fairly normal solar wind parameters for a certain amount of time that are basically meant to condition and establish a fairly normal magnetosphere. And then it gets out the hammer. So then a CME arrives with compression factor of 4, so it's going from 5 per cubic centimeter to 20 per cubic centimeter. It's 3,000 kilometer per second launch velocity off of the sun, so slow down to about 2,700 locally, with 127 nanotesla field. So this is basically hitting the magnetosphere with the biggest hammer you've got to see how it rings. And this is done in 2 different ways. It's done with a northward IMF and a southward IMF. All right, so this is kind of a worst case scenario that Dan presented in this paper. It's kind of building on some work that other folks have done. So if we assume that we have downloaded the data, it is sitting in a directory that we have provided for you, so we can just run this cell that just defines where it is. All right, and then you can just skip this not summer school thing because that will you need later. And this is just a whole bunch of imports, which we will blow past without describing. All right, so we have 2 sets of output data. One is from that northward IMF case, one is from the southward IMF case. And there are outputs from the global magnetosphere, which is Bats Are Us, and the ionosphere, which is the Ridley ionosphere model, and those are coupled together. All right. SWMF is not one unified code. It is a bunch of different codes that have been designed to run together and be coupled. And so you'll be looking at the output formats, and there will be slightly different things involved in each of those because it's modeling different physics. with different codes. But the idea is to present the data in a way that's common where there's commonalities and different where there's differences. So we're going to skip over those details. But then there are these base classes like the log file and the IDL file, which these are the slices of each point in time. All right, so we're going to run this. Okay, so they're based on the data model, which I presented earlier. So there's keys, there's values that have dictionaries associated with them, and there's attributes. And we can dump out, take a look at the attributes so we can know this particular one was read from this particular file. Gives you an idea of the time range that was modeled, the specific times involved. Same thing with the log file. If you look back at the MHD file, we can tell what information it has. So this is the MHD model. We've got the grid. We've got velocities. We've got magnetic fields. We've got some currents. And we can really go and dump out all of the detail here. So this is all just looking at the space data objects as well. And all of the SWF output that's handled by PyBats gets presented in this way. So you can look at these kind of high level. We'll skip those. This is the idea. So the MHD data file is, as I mentioned, multiple times dumped together. This gives us some information about that. Right, there's called frames. If you need to look at one particular time, you can select a particular frame. So this lets you know it's loaded. Starts by having the first one loaded. Gives you the information. So this gets you an idea of what's going on, gets you those high-level attributes. There are then specific subclasses within PyBats for each of the types of model output. So if you've got a file you don't know much about, you can kind of pop it open with those generic classes, start to take a look. Once you know what the output actually is from, then you can use one of those subclasses. That MHD output we now know is from Bats R Us. We're going to open it up with that and call a few things where you can calculate some B fields. And so this is dumping out our unit vectors, X component for the magnetic field throughout each of that, right? Similar, we're going to read in that, the really ionospheric model and dump that out. So the PyBats documentation, there's a lot in there. It doesn't render particularly well right now. You do want to look at the help within SpacePy, within like an IPython window to get that information. We are working on improving that. So it's out there. But do take a look at the actual help string. That'll help you figure out. Okay, so we've looked at, okay, yes, we can get some numerics out. We can get some idea of the attributes, but we really want to see is get a nice big global view, because that's why we do global codes, right? To actually see what's happening out there. So there are a lot of plotting functions that start with add, and you can potentially specify a specific figure to put it in, which we'll see later on, or you can say, please make a new figure and hand me back those figure and axis objects, which is a very similar approach to what Jim was showing earlier with PiSpeedAS. It's a pretty common thing to say, okay, you can pass around these matplotlib objects that describe where you want those figures to go. All right, so we're going to go and just get a plot of the grid resolution of the model, and then we're going to throw on top of that some contours of pressure. So we're doing an XZ cut, we're applying the pressure, doing a log plot, and we're not going to fill it in, right? All right. So this is our first interesting output. And we've got two things going on here. We've got the background color is the grid resolution. And so that's labeled over here. So you can see, not surprisingly, kind of matches because you see the grid squares, right? The big grid squares are low resolution. As we're getting in closer, where things are more interesting, the grid resolution is getting finer, so it can capture those dynamics. Then we have the overplot of contours of constant pressure. So we got the nice pressure contours through the magnetosphere, and then we got this weird thing happening here. I guess what this is? So this is the arrival of that shock, where we have the factor 4 compression. And the reason it's doing this fan out is simply because the grid resolution is dropping as we get further away. So once we're out here, the grid resolution isn't really sufficient to resolve that shock. So a pretty common thing when you're looking at a global MHD model is that you're putting the resolution where the important stuff's happening. And it's not like we care about out here because this is not actually impacting the nose of the magnetosphere. It's not going to be really driving the dynamics much. All right. Okay, so now let's take a look at more magnetospheric picture. Okay, so I'm going to show you the output first and then what makes it. So we got two things. This is, again, we're getting the pressure, but instead of putting on the grid resolution, we're putting it on top of the actual field lines. Note that our closed field lines are in white, our open field lines are in black. And then this is the ionospheric currents that are resulting from the impact of that shock on the magnetosphere. Oops. So let's scroll up. How did we get that? Well, we did a nice matplotlib, just make a figure. Then we called add contour method on that MHD object. We specified the target and we specified a location, which is cut off because the resolution on this is terrible. And we got back, hey, here's the figure, here's the axis. So that just gets us our nice contour plot of the pressure. Then we're adding the magnetospheric field lines and specifying, hey, it goes on the same plot as here. And then we specify with the same figure, but a different location next to it, those Birkeland currents. And then we just tighten it up. All right. So all of this, all of the labeling, all of the color bars and such is built right into PyMats for you. All right. But because you do have those axis objects and those figure objects come back, you can go and tweak them later if you like. All righty. So now we get the fun thing. What's happening over time? And I'm going to, again, look at the output first. And then we can see about all of the nitty gritty of Matplotlib and Pi. That brings us to that. There it's run. All right, so let's talk physics. So in both cases, both in the north and southward BZ case, at kind of as that shock arrives and hits the nose of the magnetosphere, we have a big honking compression, and it's really looking the same, whether it's with that northward 127 nanotesla or the southward 127 nanotesla. That's just pure pressure compression on the nose of the magnetosphere, driving some massive field line currents down through the ionosphere, right? So that's all very nice. Now, of course, it's massive, but it's going to get bigger because you can see the scale here is increasing. Looks pretty much the same for the northward and southward case initially. Next time step that we have in the output, also fairly similar. You're starting to see a little bit of difference maybe the exact shape of the day side. But once you get down to here, it starts to get really interesting because at this point, the northward is still pretty much just compressing on the day side. There's not a lot of interaction going on. So it's actually strengthening the field here. In the southward case, you're starting to actually get reconnection that's eroding the day side. And so you're decreasing that field strength. You're getting stronger field line currents. And then this last plot here, you're seeing kind of the ultimate result of that, where again, northward IMF, it's really just holding off, it's just compressive. And the day side magnetosphere has been more or less eaten away into very close. That's driving these incredibly massive field line currents. And so you've got here one figure that gives a really great global picture of what's going on in this particular case of a very extreme impact. And Dan isn't screaming in the chat yet? Cool. All right. So let's see how we got to this. This is looks like it's a 4x4. We're going to set it up though as kind of a 4x6 so that we can have those magnetosphere plots be bigger than the ionosphere plots, because we kind of like this to be wide, and we would rather not stretch the ionosphere to look non-circular. So I apologize for the motion sickness, but that's the first thing we do is we set up a Matplotlib figure and do some magic stuff, and we establish a 4x6 grid. Right? Then we're looping over each frame of that MHD file. So we're going to be populating a figure from top to bottom. Yeah. Can we have a microphone over?
Yeah, can you go back to the earlier figure?
Sure. This one?
No, sorry, the northward and the southward case. Yeah.
Oh, okay. So the actual.
Yeah. So over here, I'm observing that, after the arrival, like in the fourth subplot. So this is plotting the pressure variation, right, in the magnetopause.
Yeah. So we don't have an actual color scale on the pressure, but yeah, this is the pressure, and I'm pretty sure we got these on the same scale, but I'm not positive about that.
Yeah, so I'm just curious, like if you see towards the flanks of the magnetopause, you're seeing like there's some fluctuation, like high pressure, low pressure. So do you think they are resembling KHIs?
So this is not the flanks. This is an XZ cut.
Okay.
Right. So this is basically just the solar wind is coming in and shoving over the magnetosphere.
Mm-hmm.
And so really this is just the magnetopause, and that's just the difference between that very high density solar wind plasma and the fairly empty lobes.
All right, one more.
Oh, and Darren's going to tell me how I'm totally wrong.
No, I was just gonna say that for this simulation, first off, you're missing an intermagnetosphere. There's some things like that that would help with the KE stuff, but it's also, if you look at the grid resolution plot, there's not enough resolution in the areas where you would see that.
Yep.
So there are certainly other simulations that SWF has done that does definitely see those things, but this particular setup wasn't designed to look for those, and so it wasn't set up with enough grid in the right places to really see it.
Yeah, this is, thank you for pointing out, because this is just the ionospheric and magnetospheric, so we're not including the ring current and other intermagnetospheric effects.
And hey, John, while you're nice and distracted, there was a couple people in Zoom who were asking the question about the data used with this notebook. Are we actually using any of the data files we put in the Scratch space to run these notebooks, or do they run themselves without it?
This is all in the Scratch space.
All right, okay, I can clarify that.
Yeah, outside of HelioCloud. So if you're running this at home after the summer school, you can go to Zenodo to get the data. And then you skip over this summer school only section and go to the setup not summer school and just tell it where you downloaded that. And you can run that. And in theory, if you have the notebook, that should all be self-explanatory, but as Darren was pointing out, that the entire intermagnetosphere there is, a couple of grid points. So, all right. So we are setting up this nice grid here. Let's get that. Okay, and then going through, and we have the two sets of MHD outputs loaded. So we're just going to loop over them and do them one by one, top to bottom. get the time, plotting the ionosphere output here from the appropriate output file. And we're trying to get like an absolute maximum here so we can get that, get the currents on the same scale, and similarly the pressure on the same scale left to right. And we start by adding magnetosphere plots. This is using, again, Matplotlib add subplot, which gives you something to draw into. And by using that grid layout, it can go and say, okay, make this 2 wide, 1 tall. So all that's happening there. Adding those pressure contours as filled contours, throwing on those magnetic field lines. So we are just doing that for each of those cases, north and south, and then that's happening 4 times as we go through that loop. All right, then we go and put in the field line currents, again, using our grid layout, adding 2 more things to plot into, calling the add contour on the ionosphere output object there, giving it a target, and telling it the maximums. We wind up on the same plot. All right, then we're getting fancy here by manipulating Matplotlib in wonderful ways, because what we have done is we have this, again, 4x6 grid. We use 2 up, 2 up, 1 up, 1 up for this. And then we're just abusing Matplotlib to shove in that central color bar. Again, is this something you're going to be doing in this level of detail at the moment where you start opening this up and investigating it? No. But this is how you can get down to something that is ultimately pretty much something you can drop right out and put right into the paper. Right. All right, so we're making a color bar, putting a nice pretty little label on it, doing a bunch of messing around to label that for those figures, and doing some adjustments. So, and then one final label there. So most of the work here is being done in telling Matplotlib, okay, I want these color bars, I want these labels, I want these labels here. The key information of your pressure contours, your field lines, labels on that, your currents, your labels of your latitude, all of that's coming straight out of PyBats. And then everything after that is kind of your choice of how it is that you want to put this together to tell the story that you're telling in the paper. And the nice thing about this is, yes, this is a little bit more of a pain in the neck than having something where you can like drag stuff around and rearrange and edit labels, but we have this code. If something comes back from the reviewers where they say, oh, this is very fine and good, but you mislabeled this thing here, we can just edit one piece of code, rerun it, recreate the figure. Right? So you'll be pulling this together by interactively poking at it, capture what you do, and then ultimately have something that's an artifact that will nicely produce that figure for you. All right, I think we went to that. All right, so any questions on these visualizations? All right, let's loop back to being quantitative, right? So one of the things that we can do with the Bats R Us classes is pull out the MHD results, interpolate them onto another grid, right? So we're going to just switch to a particular, we're going to go to frame 2, which since we're not Fortran is the third one. So we're just pulling this frame off of the southward IMF case and to go poking around in that. All right, so we're calling MHD South, we're switching to that. We're going to say we want to have a bunch of points along that sun-Earth line. And we're going to try to find where the magnetopause is along that, right? So we're getting a line through there. We're finding the first open, last closed. defining kind of that halfway point, and we are looking at the magnetic field from the simulation here. So this is a nice cut out from the subsolar point of our magnetic field. We're coming down as we get further away from Earth. That's always good. We have a very clear transition here down to lower one. And if we pull out the last closed field line from the simulation, overplot that, that matches where our magnetopause obviously is based on the decrease in magnitude of BZ, but also, of course, the flip, because remember, we're going over to that negative case. So yay, it works. Our magnetic field and our last closed drift line match. Okay, cool. So if we did that for each of those outputs and came up with some magical way to do it for the northward where you don't have the clear sign flip in BZ, then you have this nice little pickle that Dan made. So we're not going to go into those details, but we can go, again, let's look at the physics first and then look at it. Okay, so we have over time, the extracted DST, which again, we don't have the inner magnetosphere dynamics, right? So it's not going to be quite right. And get that in the northward and southward case over time. Right, so we can get some nice quantitative stuff out there. And of course, spot the Michigan guy. Doing our plots in blue and gold. All right, and then here's our magnetopause standoff distance, which again, you start with the arrival of the shock. They're kind of the same in both cases, but in the southward IMF case, you get that further erosion of the day side, moving it in closer, but you don't get with the southward. Cool. I wish I had two things here. But you see you have that nice little pulse at the arrival. And also look at where that standoff distance comes into. We have a magnetopause that's almost touching the butt. So that's cool. So what we've got out of here is that ability to look at the individual numbers, the ability to get that nice global picture, the ability to go and do cuts that will give you some very quantitative specific line trace kind of information out of that. And the other thing that Dan's working on is all of this is working in terms of 2D cuts. He's also working on 3D visualizations of the full output. Do you have any other questions on that? Anything online? Cool. So particularly in terms of the Matplotlib figure stuff, I do really encourage you, if you have the time, go and take a look at these notebooks, go through, play around with them, change stuff around, get a sense for this, because as you're building out a figure for a paper, ultimately you do want to be able to assemble something that tells a really compelling story. Right. And learning all of those details. This is not a SpacePy thing. This is not a PiSpeedAS thing. This is a Matplotlib thing. Matplotlib gives you just a huge amount of stuff you can do with it. So cool. And please do ask us questions in the Slack or on our GitHub repository. If you've got any. I think we can go to lunch early then. That's what gets the applause, right?
Cool, thanks, John. Okay, yeah, let's go ahead and wrap and go to lunch early. We will come back by 1:30. So you've got a bit longer to work with today. And when we come back, we'll start with PySat from Jonathan. So enjoy.
So hello, everyone. I'm noting that lunchtime is over now, but here in the room, we're still a little bit empty, waiting for people to come back. So we will give it just a minute or two more before we officially resume. All right, well, that's about as long after the lunch break as I want to wait before continuing. So we'll let people who are still funneling back to the room just come in and be a little bit late. First, can I get anybody on Zoom to confirm that you can hear us? I'm seeing yes, thank you. That is good to hear. We had to restart the Zoom over lunch because we lost internet in here. So, okay, next up, we are going to have a presentation about PySat from Jonathan Smith. But first, I need to walk everyone here through doing a little Git pull to get in some updates to the notebooks that we will be seeing in this presentation here. So if everyone is hearing my voice, please pay attention for a moment because I'm going to have you click a couple things in HelioCloud. So I will say first, take a second to get to your computer and then get back to your whatever browser has HelioCloud open. And then pretty please, if you could, just go to the root directory where you have cloned the Summer School 24 folder and go inside of it. And now I'll give people just a minute to scramble and do that before I continue on. And now online people, I'm just going to be assuming that you are following along here, but everyone in the room, has everybody got to this page here yet? Or does anybody need just a second more? No? Okay, cool. All right, so all you do is there's actually a lovely Git menu item here. So if you can go to Git and do pull from remote, ideally that should work in one button click. Your current changes forbid pulling the latest changes. Do you want to permanently discard those changes? This action cannot be undone. Whoop. Well, no changes were made to there. So it would be safe. Oh, okay, yeah. Well, in my case, I am going to go ahead and discard any changes to pull them in. But if you do not want to do that, if you are happy with changes you've made and you don't want to do that, I guess I would suggest probably just doing something like renaming this to something unique and then doing another, this button here and just cloning it again. The repo was, I can post that link in the chat. 1 second.
Maybe somebody was tinkering on that one. Ran one of the notebooks that got updated.
Okay, cool. Yeah, I mean, in the best case scenario, when you were right there doing the git pull, it should just be a non-action. You just pull from remote and it just, boop, done. At least maybe everyone in the room, raise your hand if that did work for you. Great. And then if it did not work, cool. You got that? All right. Thank you. Could you please also post that in the Zoom chat? All right, the link to the repo has been added to general and Slack again. Here just momentarily, it will be in the Zoom chat. And so there you go. So you can reclone that repo if you don't want to discard any of the changes, but that will just get you some updates to the PySat notebooks that we're just about to get a presentation over. And it also pulls in a new folder for some Madrigal Web stuff, which will be later this afternoon. So I think with that, Jonathan, sorry for stealing 9 minutes of your time, but I think you are free to come on over. You know how to pin that and stuff.
Should be easy enough. And just put this in my pocket. All right. I guess everybody can hear me. I can hear me. I'm going to be talking about PySat today. So I'm going to head over to the PySat tutorial notebook. But before I jump into the notebook, I am going to go to github.com PySat/PySat and give a quick overview of what PySat is and what we work on. I do want to preface this a little bit. I'm sort of like a glorified user of PySat. None of the real core developers could make it today, so I'm sort of filling in for them. If you want to see how bad it is, you can look at the insights page here and see the commits from the thinking emoji. That's me. And you can see just how little I've contributed to this core package here. So PySat is the Python Satellite Data Analysis Toolkit. It's supposed to provide a simple, flexible interface for data analysis. You can do some data downloading, data loading, analysis. It does sort of integrates the cleaning from the quality flags in the data into the loading a lot of the time. And the way the PySat ecosystem is structured out, the sort of PySat core package does not do a lot of the science legwork on its own. It's sort of the mechanical parts in the back end. And there's an ecosystem with a lot of plugin packages that I'll go into a little bit that sort of are specialized for different data archives and data types. So the main features of PySat is it's instrument independent analysis routines. So no matter what your data file originally is or the source, we pull it down and put it into either a pandas data frame or an Xarray data frame to sort of regularize the handling of the data and make it more consistent and a little bit more Pythonic. So, this helps with standard data handling tasks, identifying the data, downloading it, loading files, cleaning, modifying the data and the metadata. It's all built into the PySat instrument object. It supports metadata consistent with the NetCDF 1.6 standard, and hopefully soon we will be adding some defaults in to make it compliant with the ISTP guidelines and make it a little easier to sort of prepare your own data sets for archival on SPDF. It simplifies data management, so it's got iterator support for any sort of data set you have, no matter how the files are parsed out. It'll do iteration by day, by file, by orbit, sort of irrespective of whether or not your files are daily files, weekly, monthly, anything like that. You can specify custom iteration intervals or custom seasons. And this line right here, supporting rigorous time series calculations that require spin up and down time across day. I'm going to be honest, I don't exactly know what this spin up down is supposed to mean right here, but if you're doing sort of rolling averages, rolling means over the data, you can pad the data so that you start at the 0th hour of your day for your iteration. PySat includes helper functions that should help you to make new instruments. So we have a bunch of instruments in PySat already, but we develop and add more instruments on a need-based basis for us, the main developers of PySat. So if you like the PySat workflow and you'd like another instrument to be in there, it's pretty easy to add more instruments in. You only have to add one file into the PySat source and a handful of functions, and then your instrument will work like any other instrument in PySat. There's some requirements and stuff, but I'm going to talk about the PySat ecosystem. So I'm going to jump over to the documentation and go over to this ecosystem. So like I was saying before, the PySat core package is really the meat and potatoes of how the files are handled. But if you want to grab data from a particular instrument, you're going to need one of the ecosystem packages. There's PySat CDAC for the cosmic satellites, PySat Madrigal, which interfaces with the Madrigal database, which we'll be talking about later today. PySat missions, it doesn't actually interface with any real data. That is for producing simulated satellites using SGP4. You can either give it 2-line elements or just some basic orbital parameters like eccentricity, apogee, things like that. PySat models is for models. So if you want to use a model like a PySat instrument, you would use the PySat models ecosystem package. PySat NASA is for interacting with the CETA web archive. Space weather pulls data from a few different archives. One of them is the NOAA Space Weather Prediction Center. And then PySat Incubator is sort of a package if you wanted to create a new instrument or something. That's the place to go to look for sort of walkthrough on how to do that. There's a little bit of analysis tools. The missions is for producing fake orbits and models, and then seasons is for doing seasonal averaging, medians, binning, things like that, sort of automatically. If I go back to the GitHub and go to the main page here, there's some tutorials here. These will be updated soon after this workshop with some updates from what I learned here. And then there's this PySat ecosystem template. If you wanted to make another one of these ecosystem packages for, say, SDAT or something like that, that would be the place to go to learn how to do that. So I will jump into some notebooks. Are there any questions about the overall PySat ecosystem? All right. I'll start with a really basic example. So this is the O1 ACE SIS customization. Yeah. Nope, that's the wrong one. Okay. So we'll have to do some basic imports here. We're gonna need some date time handling, NumPy, matplotlib to customize our plots a little bit at the end. We'll import PySat, and then we're getting ACE data, so we're gonna need PySat space weather. So import PySat and PySat space weather. So when you download data with PySat, it needs to put it somewhere. PySat does not just use cloud-based data. Basically, the way the PySat paradigm is organized, anytime you want to do any scientific analysis, it will download the data you want to look at in whole. This has some drawbacks because you're using a lot of storage, but PySat is designed around a lot of closed system processing. So, we often are working in systems that are offline or with data that is not available. And PySat is sort of made for any of those situations as well as downloading data. So this second cell here is a lot of checks because I was having some problems with the notebooks in making sure that the download directory was set correctly. So this is just a big long-winded way of setting the PySat.params data dirs. So setting the directory where we're going to have all of our data downloaded, and it should already be downloaded into the notebooks for this. You can see that there was originally nothing set, and now we set the directory to this .PySat hidden directory in Scratch space, where we have all of the data files we'll need for this. Just another check. I can't be too sure. And then in order to make PySat work with the ecosystem package, we need to register the instruments. So we got a utility, a registry utility, and we will register by module the entirety of the space weather collection of instruments. So now PySat knows about all the instruments that are included in the PySat space weather module. So now we need to make a PySat instrument. This is where we will instantiate the PySat instrument. We'll give it a little information. We're using the ACE platform, so the ACE, and then the SIS instrument. And we're using historic data. So you have to give it that information there in the tag. And now that we've made that instrument, there's no data in it yet. It's just a PySat instrument. And let's get a little information about what that ACE PySat instrument is. So we get a long name. This is something that is in the PySat space weather package by default. So this is not coming from the metadata of the files. We've got some basic information. The platform is the Advanced Composition Explorer. The name is the Solar Isotope Spectrometer. We've got this tag, and then it tells you all the available tags. There's also the real-time tag if you wanted to use that. This is not the ascientific data set. So a little note about that. This is not what is on CEDAWeb. If you want the ascientific data that's on CEDAWeb, you'd need PySat NASA. Little information, real-time data, and historic data, sort of describing what those are all about. This is an important part here. One of the functions on this is clean. So the ACE instrument supports real-time cleaning of the data. You can give it either the clean specification or the dirty argument, and it will choose a different group of quality flags to use to sort of accept or clean out the data. It'll pare the data down. So in this case, we are deciding what's clean and dirty here, but you can specify your own cleaning sort of parameters. That would require a little bit of extra development, but we would welcome that, basically. Some of them have a lot more cleaning options than ACE. For the needs of this particular developer who wrote this, they only needed either, the pure good data in the quality flags, or they were willing to accept a lot of things. But for instance, Like the CNOS IBM data has like 4 or 5 different clean settings. So yeah, if you're looking at this data and you would like to have a different collection of quality flags run through, please let us know. That's a pretty trivial task to add in. Yeah, so this one is returning a pandas data frame, sort of when it's going to be pandas and when it's going to be X-arrays, depending on how high the dimensionality is for that particular data set. So a lot of the older data sets in PySat are going to be using pandas data frames. Newer ones will be using X-array. Here's a little information about these functions. This is a little opaque, I think, but it does tell you some information, especially if you're debugging a problem. This can be pretty useful. All right. So one thing about PySat instruments is you can attach custom functions to them that will be invoked on load. So when you load the data in, the function will be automatically applied to the data set. So that might be a function where you want to add a new data variable to the instrument based on some calculation between the existing variables. And the reason we would want to attach this beforehand, if you're exploring the data and you're trying out new things, you probably wouldn't want to do this. But if you have sort of established processing routine, you can define a bunch of these functions and attach them in a particular order and keep track of the order of operations on your data as you're processing it. So this is calculating the ratio of 30 megaelectron-volt to 10 megaelectron-volt flux. And we're then adding some new, this new ratio variable into the instrument. And then it's also adding a bunch of new metadata for this new variable. When you write these functions, you have to give it just the instrument as the input, and then a simple return closes that out. And then you attach it to the instrument by using this custom attach function onto the instrument object. And so now we still haven't loaded any data. We've just set this instrument up. It's ready to take in data. Normally you would have to download it if you don't already have it. We don't need to do that here. It should already be downloaded. And now the moment of truth, if we run the 9th cell, we will load the data. You should get this warning. This use header keyword argument isn't necessary anymore in PySat 3.2, which is what we should be using here. I just want to make sure that cell 9 worked for everybody. If anybody can tell me that did not execute for them. You got an index error? That is not great. I'm not sure what did your PySat parameters come out with is anyone else getting an index error on that one? Oh, okay. Hopefully Sean can help with that. So now that we've downloaded the data, we will sort of just print the representation. So again, we have this platform, the name of the instrument, the tags. Instrument ID is an optional keyword argument that we didn't need here. We get the cleaning level, whether or not we use data padding, and some basic information about the local files. We have 31 local files. Here's the date range of the files that we have stored locally. We have some information about the day that we loaded. We only loaded a single day. We get the time range, how many variables there are, how many time steps there are, and then a little bit about the meta. Only have 7 metadata values for 7 variables. There's 0 global attributes in this data file. I don't like that, but I didn't make this data file. So Now we'll just do a quick plot. We'll just be using the fact that this is a pandas data frame to just use the pandas plotting. So there's no custom plot routines in PySat. We will be getting the units of these variables from the meta object, which is one of the elements of a PySat object, PySat instrument object, I mean. And then we'll be getting the name of it also from the metadata. And so we're just going to iterate through all of the variables in this instrument. It doesn't have a lot. And we will plot each of them and automatically get the units and the name for the title. So we're getting that ratio that we added, the proton flux, integral proton flux at different energy levels. And that's it. We only have 3 variables here. So it's a pretty standard first grab of some data to look through it. We added a custom function that was run on the way in. Yeah.
So SIS has way more data than this normally. So how does it that we only grabbed these few variables?
That is a good question that I do not know the answer to. Probably because of where this, because I mentioned earlier that this is not the ACE, this is scientific data.
Okay.
This is the space weather data.
Okay, yes, that makes perfect sense.
I don't know a lot about ACE, so I hope that answers the
Yeah, it
question.
answers everything.
Yeah, this is coming from the Space Weather Prediction Center. Okay. So we'll move on to DMSP. The first few of these notebooks are just sort of using a bunch of different data sets and some basic plots. Most of the plotting here is just using matplotlib. Nothing really to do with PySat, but just showing sort of instantiating these objects, grabbing the data, using it with PySat. PySat fits in those first steps. It makes managing the data files on your local machine pretty simple. Here are a bunch of imports again. Now we're using PySat Madrigal. So we're interfacing with the Madrigal database in order to get the DMSP data. We do have this warning thing here. This is a deprecation warning that we have in the current version of PySat that will be fixed in the next minor version. And again, setting that data directories parameter just to be sure that we're looking in the right place. Now, this is the first time that we've used PySat Madrigal, so we need to register the PySat Madrigal instrument with PySat. So do that. This is a small warning. We don't have the right metadata here, but it's just a warning. It'll be all right. So we're going to look at IVM or ion velocity meter data from the DMSP satellites. We're going to be looking at the F-15 satellite. So we'll get a date that we want to look at, and then we'll instantiate this instrument. So the platform, the satellite, is DMSP. The instrument on board that satellite is the IVM, the ion velocity meter. The tag for this is UTD. And we'll look at the other tags that this instrument has. And then the InSight is F-15. It's multiple DMSP satellites, so we want to grab F-15. Then we'll get the help on the IVM inst module. So there's some basic description. It's only this one tag, and then there's this one. I don't actually know what the nothing tag would return that's different than UTD. And then here are all the different satellites, the different DMSP satellites that you can pull data from. Here's the example that we just ran. You do need a username and password on Madrigal, but to download, but you don't have to actually give it a real one, but they would like a real one so that they can keep track of who's using the data. So for this case, you can supply the download with your first name and last name and the password. Here we also have some sort of prescribed cleaning levels. So we've got a clean, a dusty, and a dirty. And so now dirty is anything under 3, dusty is sort of in the middle. And if you want to know more about the cleaning, that should be in the metadata for the quality flags. So what exactly these quality flags refer to. You can also pass none to PySat clean if you want to have no cleaning done and completely ignore the quality flags. That is always an option. And then there's this download routine. So this help is just going to tell you pretty much everything about this particular instrument, anything you could want to know. And now the DMSP loaded data, where's the, haven't loaded anything, but that's okay. We don't need to download. We already have it. So we're defining a custom function here that's just going to pull out the Northern Hemisphere locations on DMSP because that's all we're looking for. We want to look at over the magnetic north or magnetic pole. And so this will modify the data as it comes in to simplify the plotting later on. So we grab the indices where we're interested, and then we basically reduce the data down with those index indices. Here we attach the custom function to the instrument. If you don't attach it, it won't do anything. This is a built-in PySat Madrigal analysis data or function. You can look at these in the methods, help and get a list of all of these built-in functions. And again, we're doing another one of the built-in analysis functions for DMSP, adding drift unit vectors, and one more, adding drifts to the polar cap in X and Y. So we've defined one custom function, and then we've used a bunch of the built-in functions for PySat Madrigal. Now we're going to not download the data, but this actually has a check to make sure there's not already data in your archive before it even tries to download. And then we'll load the data into the instrument. Looks like we've got a lot. It's taking a moment to load in. So we've got it. Let's print the information. You should be able to skip this 7 cell if you don't want to run it. Sorry. So we got all this information again, DMSP, IBM, UTD, the clean level we used when we downloaded the data. And then this has the order of operations, all the custom functions we applied. So it tells us first, we selected for the Northern Hemisphere. Then we smoothed the ram facing drifts. Then we added the drift unit vectors. And then finally, we added the drifts in the polar cap, X and Y. So you can tell what order you did these custom functions in. And that helps you keep track to make sure that your analysis was performed in the right order for those analyses that depend on a particular order. Okay. So now we do have some global attributes. That's nice. We've got 41 variables here and 7 metadata values for each of those variables. We're going to make a quick figure to plot the orbital passes across the polar cap. This is all just matplotlib right here. So we're just making some subplots, which is one, I guess, and setting up the axes for a plot over the pole. We are getting the spacecraft location in polar coordinates for plotting here. So we're getting the magnetic local time from the IBM instrument, converting that, and then getting the magnetic latitude and converting that for radius here. Get the magnitude. You know, none of this is PySat specific. We're using NumPy square root and just taking the magnitude of our ion velocity, doing some quick slices here to mask where it is nan where we have NAM values in our data. And then we're going to do this quiver plot to get the direction of the drift along the satellite track. Fixing up the title. And you get this sort of standard plot of these drifts over the pole from the DMSP satellite. It took a little work still to do these sort of simple conversions. These are not going to be part of PySat. These are a pretty standard thing. PySat's really just preparing the data for you so that you can do your analysis on top of it. Yeah, I'll jump over to yet another example. So another IVM example. This is coming from Icon. Do our imports, set our directory. Now, to get Icon data, we need to look at CDA Web. So now we need to use the PySat NASA ecosystem package. So we'll import PySat NASA, register all those instruments with PySat, and then we'll make an IVM instrument from the IVM onboard Icon. Icon actually has two IVMs, so we need to specify that we're looking for IVM A. We'll use the clean data, so that'll only be looking at data with the clean quality flag. And then we will get some help on the IVM inst module. So this tells us our platform and our name. No, it doesn't support any tags. You have two instrument IDs. Another example, some example code in here for using the IVM instrument. And the basic functions, so there's clean, there's filtering the metadata. You have a load function. All the attributes, the things that you get out of it. This one is another pandas data frame. So any pandas functions or functionality will work just fine with this. We'll set a date range to download the data and to load the data. And here is the information on downloading the data. It's all commented out because we're not downloading anything right now. We don't need everybody downloading all this data today, and it's already in the notebook. So you can get a little bit of information about the downloads. Normally, if you hit download, it'll just won't tell you anything. And when it's done downloading, you'll get a new input line or whatever. But if you want to see what files are being downloaded and when, to get a better idea of what is happening behind the scenes, you can set the PySat logger level to info. So PySat has a logger and there's several settings, and it'll tell you more and more information, be more and more verbose about what it's doing behind the scenes. And so, yeah, and then this would download. You can download a bunch of different ways, and I'll get into that in a little bit. But we're not using that today. So we'll just do a really simple density plot of everything that we load in. So we're going to load in a single day, the first day of 2020. We make another instrument for some reason, and we get we're going to look at the ion density. So this is a pandas data frame. So that means each variable is a pandas series. So you can just put a dot plot at the end of it, and it'll plot something. And that'll return a matplotlib object. We will manually set the title and the labels here. And we will then, in another figure, plot the log density. This will take a second. And here you go. That's a day's worth of density data, but you might not want to look at a whole day. You might want to look per orbit. You might want to look at a specific range. This, you can just sort of see the periodic changes of the density over every orbit. It's going through all the local times. So you're coming through, noon, right over the crest and ionospheric density every day. But you might be interested in looking per orbit to get a sort of closer look. So you can do per orbit plots pretty easily, even if your data set does not have an orbit number in it. PySat will determine orbits the way you want it to. So it does orbits based on longitude, local time, magnetic longitude or magnetic local time. And so here, to do that, you need to specify some information about the orbit. What kind of orbit do you want? So the kind is going to be a local time orbit determination. And then you have to know the name of the variable that has magnetic or has the local time in it that you want. So we're going to give it magnetic local time to determine the orbits. So it's going to look for, the sharp gradients in the magnetic local time and use that to determine the orbit breaks. So now we're going to instantiate a new instrument and give it this orbital info. So we have to give it the platform, the name of the instrument ID, our clean level again, and how to break out its orbits. We'll give it some boundary. Because we're going to be iterating over the orbits, it'll just keep going through all of your data if you don't give it a clear boundary. This none at the beginning of the bounds means start at the very first file that we have in our system. So it will start at the very beginning, the very first file in terms of date. And then we're going to give it just one extra day here. So we're going to only look at one data, orbits from that one day of data. We'll load the data, and then we will start iterating over those orbits. So for every orbit, you get a sort of temporary instrument in the IBM orbits. And we will only be looking at one orbit so that we don't have a ton of plots or a lot of messy lines over each other. And we will just plot the log 10 of the ion density and give that a title. That'll take a second. So that's just for one orbit. So we're looking at 23:30 to 1 o'clock the next day. We're looking at the log density and why do I have multiple plots here? Different days. So he's got the first orbit from two different days. We could add a couple on here, get a couple overlapping. I don't know if this is going to work right, but no, that did not work. But normally you can iterate through the orbits and you can get a lot of different variables, and we'll be doing a little bit of that in the Komodo PySat combination talk. So if we want to look at, we'll add the log density now as a variable to the instrument as a custom function. We'll set up this orbit info again, the instrument. We'll give it some boundaries. So now we're just going to do one day. We'll add the log density in a custom function. We'll attach that custom function, create a figure, and then we'll plot a few different variables for this orbit. We're only going to do one orbit again. So here, when we're iterating through the orbits, for each orbit, you get sort of a sub instance of a PySat instrument. And so we're plotting, just using the pandas plotting, giving it our X and Y variables and setting all of the titles and labels manually. And so this is one orbit with a lot of different variables. We got the ion density, the O+ fraction, zonal ion velocity, field aligned ion velocity and meridional ion velocity. You can see there's a lot of gaps here, particularly in the velocity data. If you're interested in that, go look at the quality flags here. The IVM drifts are pretty temperamental, and you get a lot of bad quality data, especially at certain local times, and when the density is particularly low. So if you were to go in and check the quality, like plot the quality flags over here, or try a dusty or not cleaned version of this instrument, you'd see just the messiest data right here. Okay. So that's IVM time series data, but what about imaging data? What about a different type of instrument? We'll look at the MHD instrument from ICON as well. I'll blast through the imports here, setting up the data DIRS parameter. We already did this, we shouldn't need to do it again, but just in case you're doing these later out of order, we'll register the ICON MHD instrument with PySat. And now, first, we're going to get the MHD data from CEDAWeb. So the MHD data is broken up into a few different data sets on CEDAWeb. So we're going to make a bunch of different instruments for the different kinds of MHD data. So here we've got the vector wind from the red line. We've got the vector wind from the green line. We've got temperature from MHD A and MHD B. So there's a pair of MHD instruments. And then we'll make a collection that I don't think we do in this example, but you can create a constellation of them and have a single instrument that contains all of these sub-instruments. We'll look at information about the MHD instrument list, just the first one. So we're looking at MHD BW red. So looking at the ICON platform, one of the MHD instruments. So the tags you could give it are line of sight wind green or LOS wind green, wind red, vector wind. You've got vector A or B as your instrument IDs. This one does not have cleaning parameters. So if you wanted to clean the data, you would need to look at the quality flags yourself. If you want to use MHD data with PySat, please add in some cleaning default. An example code if you need one, and a little bit of information. Currently, the red and green data products are bundled together and zip filed on the server. So that means when you download, say you just wanted the red products and you went to download that, you would get the green ones automatically. So you be getting almost twice as much data as you'd be expecting in your archive. This might not be true anymore. SPF might have fixed that. But I can't say for sure what's happening on the SPDF archive right now with the MHD data. Moving through all this information, get our date range together, more downloading stuff that's commented out. Basic winds example. So we're going to set some parameters here for the plot that we're going to do later. This will be the minimum wind we want to look at, the maximum wind velocity. We'll get the red and the green data, and we'll load those in for the second day of 2020. And then we will plot it. So we are using the sort of directly from the PySat instrument. We're looking at the zonal wind variable. And to plot this in a way that'll look nice for us, we need to transpose it. And we're giving it that minimum and maximum velocity value that we wanted to look at, and giving it some manual title information, some Y label. We will do another one with the red line, meridional. So this is the zonal wind, and then we'll also look at the meridional wind at the same time. We'll be plotting lots of zonal and meridional winds. And this is just for an entire orbit. We're not down selecting at all. So you can see this sort of the cadence of the satellite's orbit through this data, very stripy. You might want to look at that a little closer. And then we'll look at it per orbit, because that is just a lot. I mean, could be useful. So we'll pick a line color for this one. We're going to do an orbit info so that when we use, now that we're moving to using orbit info, we're going to have to re-instantiate our instrument. We're also going to add an average local time variable to our instrument, because we want to be able to plot our profiles over a single local time, even though they happen over some small time period. So we're just going to give them a single time to sort of clean up our plots a little bit. We'll instantiate this instrument, give it some orbit info, give it some boundaries so that we don't iterate beyond what we're interested in. We'll attach this function that gave us this new average solar local time variable, and then we'll create our figure. So I'll let this run. The way we're doing this is we're iterating through the orbits. We are enumerating the orbits so that we have a little index here. We're just using that so we can break off after a few orbits, so we don't plot all 15 or so orbits that you get in a day from ICON. First, we're plotting the zonal wind, then the meridional wind, and then we're plotting something else. Oh, I didn't need to run that again. So we're getting the zonal wind for a few different orbits. So this will be the first orbit. This file starts at this time, so the beginning of the orbit starts around here. Finally, a full orbit worth of data. This one is actually because of quality flag issues. So many quality flag issues on the ICON data. And then the meridional wind, again, we start late. But here we can look at the wind scans from MIDI for a single orbit. And this is based on local time, so you can see the winds during the day near noon, and then our post-midnight and post-sunset winds over here. And you can do this for as many orbits as you want throughout the MIDI data, or any data set really. We'll do something similar with temperature. So we'll be doing orbital work, so we need an orbit info. We're making the instrument. We give it some boundaries, and then we're going to add this custom function to get a tangent local time, so the local time of the tangent point of our remote sensor. We'll attach the function, and then we'll loop through some orbits, and we'll plot some temperatures over a few orbits. I think 2 orbits, it looks like. So we're doing this over a couple of days. So we've got an orbit's worth of temperature here, organized by the local time at the point of the measurement, not at the ICON satellite. So yeah, it's pretty easy to drop in new variables into these instruments, and this can be done sort of before loading as part of a long-running processing routine. PySat was used in the processing for some of the ICON data, so basically they knew they were going to be getting data streams in from the satellite, and then they needed to process it all the same way, and then output it for archival. And so having the custom functions attached before the data is read in makes it pretty simple to keep track of the order in which the functions are used when you attach it to the PySat instrument. All right. So I was just talking about processing incoming data and then getting it ready for archival. PySat is sort of netCDF heavy. So any instrument that you have, if there's data in it, you can export it to a netcdf, and it will already have every variable automatically gets the sort of netcdf for required metadata attributes added in. They're not always necessarily populated correctly. So if you are preparing something for archival on something like SPDF, you will need to, double check that all your metadata is compliant. But this gets you set up sort of a template for all your variables. So we'll import PySat and netcdf4. We're going to be using some test data here. So first we're going to come up with a file name for our output data. We're just going to give it some basic string formatting here. So we want a 4-digit year and a 3-digit day of year. To specify our demo test files here, we're going to come up with a date. The first day of 2009. We're going to instantiate a testing instrument. So PySat has a few different sort of dummy instruments that you can play with. Testing is one of them. There's testing 2D, there's testing model. I think there's an ND testing as well now. That is not in this tutorial, but it is a part of PySat. So if you have a really highly dimensional data product you're working on and you want to run some tests, that is built into PySat. So we'll create this test instrument, and we will load the test data. The way the test instrument works is it sort of makes fake data to load in. So kind of have an idea of what you'll be looking at in terms of the structure. This part's a little complicated, a little longer than I really want to go into, but when you are creating a new instrument type, a new instrument file, you can create these metadata translation tables. So for instance, if you're working with a file that has a particular metadata standard and you want to go to another metadata standard, you can give it a dictionary that has the conversions you might want. I'm trying to think of a good example. I mean, fillval is case sensitive for SPDF and netcdf, but they're different, and you can't have duplicates when you submit to SPDF, or at least they'll complain if you do. So you can have these tables, and you can give that to it, and it'll automatically sort of translate all of your metadata from one standard to another. Right now, I don't think we have any. We only have one template, which is from netcdf for standards to ISTP standards. So if there are other metadata standards, we would love to have those included for some default tables. You can add new metadata, you can drop metadata, and there's a whole section of the documentation about working with the metadata. Meta is stored in a PySat instrument as its own sort of object attached to the PySat instrument that works. It's basically a dictionary, but it's got some extra bells and whistles so that you can modify it and change it. And you can also set it to be immutable if you don't want it to be changed. So you have a little bit of control over how the metadata gets worked with. In this case, we're not really doing much with the metadata. We've chosen not to drop any labels. We're not giving it a meta translation table. We're not giving it any sort of translations. We're not putting nans in for fill vals and stuff. But we are going to add a header. So this is a global attribute basically to the meta object. The new attribute is demo thing PySat style, and it will just be yes. Then we can write the file. So we need to format our file name. So we have to tell it sort of where we want it to be, the type of file path, the file name format that we're using. And then here we'll just write it to a netcdf. So first we want to get the data path just to make sure we know where we're looking. So PySat instruments in the archive always have the same format for the directory structure. So this is our archive that we set, our data drs for RAM. And then because this is a testing instrument on the platform PySat, we get the PySat directory and then the subdirectory PySat testing. And so all of our testing instruments that we make here and modify and save to netcdf will get placed in this directory. Yeah, so now we'll just look at that netcdf file that we made. First, we'll look at it using the netcdf4 package and make sure it opens up and looks like a netcdf4 normally would. So we look at our global file attributes. Here's the one that we added a moment ago. So that wasn't there by default. And then some basic information about this file. You get to know the PySat version that this file was made under. Very important if you end up trying to reuse an old PySat netcdf on a new version. If you have any issues, you can look right here and find out if it's just a version compatibility issue. You can see that the metadata convention is the simplified SPDF ISTP convention. We get the platform, the name of our instrument, some acknowledgements, sort of the date range of our file here. And now we want to look at the variables and the variable attributes. So looking through, just using the netcdf4 package to look at this netcdf. Here are variables. You can see this is that simplified ISTP standard. So this has most of the metadata that's required for ISTP, but not all of it. So you can look through that, but you don't have to use netcdf4 to look at a netcdf4. We can use PySat to look at it in the PySat way. So we can get the data and the meta that would be attached to a PySat instrument based on this netcdf. So we give it that form of the file name that we used earlier. So this is sort of not instantiating a PySat instrument. This is just if you want to hard load a netcdf and see what PySat would give you with that. So you've created a new data set and you have it in netcdfs already, and you want to look at what PySat would do with it if you made that into a PySat instrument. This is a good way of taking a look at that. So we're going to load it into pandas. We're giving it, oh, this is none. We set this to none earlier. And drop labels we also set to an empty list. So it's not going to drop anything and it's not going to translate the metadata. It's just going to give it to us as is. And here we have all of our variables, their units, long name, notes. So all those basic metadata descriptions. And then if we want to look at the data, here's what the test instrument gives you for data. You get a lot of sort of junk numbers in here that are just random number generators. We have this date range going from 0 to 2359 on the 1st of 2009. Okay, now let's see what happens when you load it into a PySat instrument. We know it's a PySat netcdf instrument. Or we're using this netcdf now. It was a PySat testing. We'll load it in using a PySat netcdf instrument. We'll update the files. We'll use all these quargs. And we'll load in the only data we have. And it is not working, which is good. Let's see what I get down here. Scratch space. HDF error. It could be. Okay, yeah, thank you. Okay. So yeah, we've loaded in the data. We're just looking at the instrument data. This is basically the same thing as this previous slide where we were printing the data output from the LoadNet CDF. And it looks the same. And we can also look at the meta again, just a few different ways to do the same thing with this net CDF we made. So that's working with the net CDF. That's mostly useful if you're making your own data sets and you want to use PySat with them, have them work the same as other data sets that you're using PySat for. Or it can be pretty useful for preparing to go to SPDF. SPDF has some tools for that already, but this can streamline it and make it a little more Python interactive. Okay, so now for one of the sort of more fringe cases, the PySat missions orbit simulations package. So I briefly touched on it before. PySat missions uses SGP4, which is an orbit propagator, to sort of produce dummy data sets, dummy locations for simulated satellites. You can use TLEs from actual satellites that are either have flown or are in orbit, or you can just give it basic orbital parameters if you want to see, quickly what'll happen if we have a few different orbital parameters for a mission that you're planning. Particularly useful if you want to fly this through models. You want to try a bunch of different orbit configurations, and you fly them through, say, SAMI 3 or something, and see what you might expect from that data configuration if you can resolve certain time scales and spatial scales. So let's do some basic imports. We're going to need Apex Pi to do some coordinate calculations. Looking at this directory, we will register the PySat missions instruments here so that PySat knows about the instruments that we're going to need for this. We will define some orbit information here. We're going to do a local time type orbit using magnetic local time. We'll set a period of about 95 minutes. So that's how periodic our orbits are. We need to set that because this isn't a real satellite, so we don't know how fast it's flying until we tell it. Now we'll make an instrument. This is going to be an SGP4 type instrument. So we'll be using the SGP4 orbital propagator to sort of predict the positions of our dummy satellite. We'll give it that orbit information, and then we'll give it a really simple inclination and periapsis. So if you only give it a periapsis, it will assume it's a circular orbit. You can also give it the apoapsis, and it'll also assume it's a circular orbit. If you want it to be an eccentric orbit, you need to give it both of those parameters. We'll get some help on this. So this is a missions platform, SGP4. We have a load, and here's all the things you can give it. You can give it periapsis, apoapsis, inclination, right ascension of the ascending node, arg periapsis. I don't know, I'm not that good about all my orbital parameters, but everything that SGP4 can take in, you can give it here. And then you can define your orbits however you want, and it'll propagate it out over time. This is pretty useful if you're trying to really quickly also figure out when your satellite's going to re-enter. So we will add a built-in function onto our missions SGP4 object here. And so we'll add quasi-dipole coordinates. Again, we can look at all of the methods by looking at the help on those. We're giving it we're hard coding a few labels for some of the parameters that we'll get out of the dipole coordinates. And then we will load a day of simulated spacecraft data and we will plot the MLT for that simulation. This will take a second because first we have to load it, which means we have to create all of this data using SGB4. And then once the data is sort of created, it'll add that extra dipole coordinates, and then we'll plot it. So we get MLT versus the epoch for the simulated spacecraft day. Nothing exciting here. It's what you'd expect as you orbit around in the circular orbit. You're going to get a pretty consistent change in the MLT. So let's look at the data in a little bit of detail before we look at the orbital analysis to see what sort of variables we have at our disposal. We've got our position in a few different coordinates. We've got our basic lat long, geodetic, and then some extra variables. I don't know what QD lat is. But we'll look at the orbital analysis. We'll just look at one orbit. That's what this break is doing. It's just breaking it down so we don't get multiple orbits. We're just plotting MLT. I forget what the default cadence is on this. We might have made way more data than we needed to for this kind of thing. You can set the cadence of the data. So if you want it every second, every millisecond. And here's our MLT versus latitude for our simulated spacecraft. After the orbit, you're only going to get a single orbit's worth of data once we load in that. So that's pretty important to recognize in the scope. If you're using orbits and then you want to go back to not using orbits, you'll need to be cautious because once you load in a single orbit, that's all you're going to be looking at in the PySat instrument. If you're doing that, you can manually iterate through orbits by using this next function. That will just load in the next orbit of data into your instrument. So now we'll look at the MLT versus epoch again for a single orbit, just a straight line. So yeah, this is a bit more interesting when you're flying it through a model, but you can try out a lot of different orbital configurations, constellations, and sort of look at where they'll be at certain times using SGP4. Maybe one day we'll get a GMAT plugin for this and have slightly better orbit determination. Okay, now was it time? Oh, great. Thank you. Well, I don't need to get to all of these. I'll just say the PySat seasoned, it just does seasonal averaging. It's pretty straightforward. You give it some bins. Just get down to that. So this is PySat seasons right here. This is a median 2D. You give it your starting and end and how many bins you want. And you have to tell it what parameters you want to do that binning in. And it'll just go through all the data for the range and it'll collect all the data and perform the calculation for that particular quantity. So for median, it actually has to load in like all the data for the median, but average is a little more performant. I won't get into it. I knew I'd have too many notebooks, and that's okay. You can go through these at your own pace and ask questions. And if there's any problems, please raise issues on the GitHub. And if you would like to make changes to the GitHub, as someone who, like I said, is a glorified user, it's very easy to modify PySat. Adding an instrument is maybe an afternoon's worth of work. There's a lot of templates already set up. So if you have an instrument you want to use in PySat, or if you want to make a custom one for some data set that you're working on, please, we'll help you with it. And it's pretty straightforward. Thank you. I assume there's no questions because nobody was asking their hand. Is there anything on the Zoom?
No questions on the Zoom. You
Okay.
do have one in your PySat Slack channel that you might go look at after this.
Okay, yeah, I'll check it out. Thank you.
Perfect. All right, thank you, everybody. We are now going to start how long is this break? A 30-minute break? Yep, we're going to start a 30-minute break now. And then when we return, we will be learning about Komodo. So thank you. What's going on up here? Everything is just completely mirrored. Everything's completely mirrored. Yep. I'm using slides. Slides. Okay, hello, everyone. Gonna get your attention back here. We are now at 3:15, so it is time to introduce Darren with Komodo. And I don't have much else because I was not normally the person introducing people, so I would just say take it away, Darren.
All right, then. All right, so if you go to your Summer School 24, the Komodo tutorial, there is an ordered list of separate notebooks that we'll jump through here. I'll try to go through these a little bit quicker because I added some fun ones at the end that actually get into more interesting things that based on what I've seen with some of the other discussions we've had here. So just to introduce what Komodo is, so Komodo's a NASA-supported open source that functionalizes data, okay? So we can access, interpolate, visualize things, but that functionalization of the data is a really important thing. And if you want to learn more, just to throw this out there so you can look it up later, there's our GitHub. Like a lot of packages, Komodo is broken up into kind of a core part and kind of the add-ons. And so there is, we have followed that same pattern, some of the core functionality and some of the other things. So if I jump into kind of a functional API, again, this is kind of a really basic starting, but it's taking a set of numbers. It's putting some decorators, metadata wrappers around that, and having something that you can then work with as a function. And that function you can interpolate in any space, any location, or whatever dimension you have. It could be a 30-dimensional data set, but you can interpolate in the various things. And so the interpolator is a really important part of it. I'm going to skip through this here. You can have this for your own reference, but it just talks about, what are functions and why they're important and what's an API. And I think most of you know that based on what I've seen here. So I'm going to jump ahead quickly. So for a function, one of the things that Komodo is making use of is a lot of the underlying utilization of SymPy for our expressions. And so if you just load some of these expression parsers here, and ignore the warning here, that's something unique about the online environment here. You can set an expression and parse it, and it can using the SymPy parsing. We can use LaTeX formatting, which is really nice to do, and we get a nice rendered LaTeX result. We can do it as more of a Python code where you use the **2 for the squared. We get the same result. It'll interchangeably work with either one of them. And because we're using this low-level expression function, you can do all kinds of things like substitutions, replace the x with the y, replace the x with the y minus 1, and it actually reorganizes and resorts it. So it's doing those things for you on the fly as it goes. I'll jump through here a little bit. There's a lot of low-level functionality that's available with these expressions that we can work through. We can do solvers. We can do a variety of things. And so I'm going to skim through these because just knowing that they're there, and that it has that nice LaTeX expressions to them gives it a nice fundamental layer that we can then count on later on when we go through some of these things. And so when we've done these expressions, we can evaluate them as well. We can get help on them. It's showing you what's there. We can evaluate and say, okay, f of 3 is 5. And so it's handling interpreting that expression properly. So if I jump into more of what Komodo does in the next notebook, now I want to talk about registering those functions with Komodo. So we've got these functions, but let's do something with them. So I'm going to import the basic Komodo, and I'm going to register this k as a Komodo function, and its f is equal to this x squared minus x minus 1. And so we've got that same function there. And we can do the same double checking. And yes, the assert doesn't give you an error. So it is matching what the actual expression was. And now we can import NumPy and make a large array of 30,000 points and evaluate it. And so you can see that f of this huge array of 30,000 points gave me back an array of 30,000 values. And so it's evaluated that function and it did that instantaneously. Komodo, again, because you're building this dictionary of functions. You can add functions to it, add more. You can add derived functions to it. It's partly why we functionalize the data sets, is that we can actually do derivatives, derived variables, a lot of those types of things, and just build up larger and larger sets of functions as well. For the most part, Komodo is agnostic with data types. However, you obviously can break it. If you throw a string at an evaluation, it's going to throw an error, and as it should. Except the error is very verbose and very very hard to dig down into what it's doing. But it basically, yeah, this expression is not a unicorn, a data type that is supported here. We can also do function composition, where functions can be functions of other functions, for example. And so we can now have a function, the function f, we make a new function g, and then we can now make a new function h, which is a function of g of f. And so you could, again, pass these arguments through here and see that, yes, these things do pass from one to the other and operate properly. So if I go to the next notebook, looking at units, in Komodo, we make use of a lot of metadata, and the units, but in our case, the units are not attached to the data. Certain packages actually attach the units as part of the package. In Komodo, they're kept in a separate block of memory. You can modify one without modifying the others. You can actually create a data set with the numbers and then add the metadata later without changing the raw functionality. But in Komodo, so again, I'm going to import this, and I'm going to declare a new function, a function of x, and this x is going to be provided in centimeters, but the result of this function is going to be a variable that's a unit kilograms per meter cubed, right? And so you've got this function, and it's going to have to follow it. And what that really means is when x is given in centimeters, I promise to return the results in kilograms per meter cubed, right? And so that's what that is trying to do. And so you can actually do this, and then Komodo handles unit conversions built in automatically as well. So I can look at the metadata. The metadata says, hey, here's the units. Here's what the argument is in this units, but the return is in this units. I can look at the detail. This will be something that will come in handy later. If you're working with a complicated system, you can actually just type the Komodo object.detail, and it'll actually show you at the left-hand and the right-hand side all the units, all the metadata that go with that along the way. And again, we're going to keep asserting that we're matching the right thing. So in unit conversion, so now I've got this other function where I've said I have this new function, g, which is a function of x, but now x is in meters, and I want to return things in grams per centimeter cube instead. But it's going to be equal to f, the other function. And so what it's done is it's actually determined that, oh, I've got to multiply the x by 100 here. I've got to divide by 1,000. And therefore, when I provide it in meters, it's going to give me back the result in the units that I want. So you can do a lot of different things. And again, here's a verbose description of what that's trying to do. All right, so let's jump down to this next one. Unit conversion can get really messy, of course. And so you're doing another one where we're doing a wide variety of units. And you want to keep allowing Komodo to keep track of that and keep going on its own is a very useful function. Here's an example where I've specified a units that aren't consistent. And so it'll say, hey, you can't convert centimeters to kilograms, because I've said I'm going to provide x in kilograms. Well, this f function expects x in a unit of length, and kilograms is not a unit of length, and so it can't do that, and it throws out the error that you see there. So Komodo keeps a unit registry, which is a way of keeping track of all these pieces. And so in this particular Komodo object is actually keeping a list of, hey, these are all the functions, these are all the units that I'm passing in, the units it's expected to return in, and it keeps those all together and does all those conversions for you. So as a little example here, just computing a gravitational acceleration, you can actually define that I'm gonna ask for the mass in kilograms, the radius in meters, et cetera, and you get your units back the way you want them. And because this is a function of two variables, if I'm gonna send it in a mass in kilograms and a radius, I'm gonna get back the value that I expect to get to this because it's doing all of the unit conversions for me as expected. And so you can see that if I define another gravitational constant, but this time I want it to be returned in different units instead of now it's in centimeters per second squared. You can see that it did all the proper conversions at each step of the function as it went through. Okay, so that's a very quick fly through of kind of the low level of what Komodo is assuming, what the Komodo core is working with. I'll show you now quickly some of the what we can do, what we're doing with visualizing. Komodo is using extensively the Plotly graphing library. I know Matplotlib is very common amongst a lot of these packages. We have chosen to go with the Plotly library. Very interactive, zoomable, rotate, probe, lots of cool functions to them. And so we've made that our core package here. And so it has backends that support a lot of different things. Another nice feature about Plotly is that it very trivially can export an HTML div that you can embed into a web page. So your graphics and your plots can have a web presence as well pretty easily. So I'm going to import this Plotly graph objects now, and I'm just going to throw a few data points at it and make a little scatter plot. And so you see, here's my scatter plot. If I move my mouse around, it's showing me the values where they are. I can actually, zoom in on a section of it, jump back out to where I was, et cetera. So this is now a nice little plot. And so I can actually take this figure that I've created. Now, the nice thing about Plotly as well, these figures are fully editable. If I look at the data that's in that figure, that's just these scatter points that I gave it. And the layout is just telling me what did I give it for a title, et cetera. And so Plotly has a host of ways of customizing your plotting as you go forward, which is something that we'll utilize quite a bit in a little bit. All right, so now we're gonna move this a little bit farther. We're gonna actually plot a function. And so now I'm going to create, again, this same function that I was using in the previous examples. And I'm going to throw a plot, and I'm going to throw, so this was just this function. I'm going to use a built-in plotting function of Komodo, but I'm going to pass it now 330 points spread across this range. And so suddenly I've now got all of these points now in a plot. And so by just calling this plot functions with that object in there and saying this is the function f, I want to plot it with these points, it'll plot those values for us. So what did that do under the scene? It did a lot of work. It evaluated the function, and it determined the argument shape, and I'll mention that a bit more. But what Plotly does specifically is it looks at the shape of what you send it and what it returns, and says this is the best type of plot you should have for that. So Komodo makes that determination for you, determines the plot type, passes a bunch of arguments around, returns the Plotly figure, and then displays it. So I can do this figure again that I've made already. I can update it very trivially, update the layout and change the title. So now I've changed the title to hello. I can update it and say, well, I want to do a fill to 0. And so now I've filled this region with white space, for example. So there's, if you go to the Plotly support page, there are a million options to tweak and modify these plot images, which is very, very nice. So if I now look at the plot types, when I mentioned before about looking at the spacing, and so for the plot above, I passed in a 1D array of endpoints and got back a 1D array of endpoints. And so Komodo has then figured out that that's a 1D line, and it's going to actually make a line plot. So if you're passing in different dimensions, you can get 1D, 2D, 3D vectors, you know, planes, whatever. There's a whole host of different automatically determined plot types that you can get just based on the dimensionality of what's sent in and what's sent out. Those can be further modified, and I'll show examples of that later. You can get a plot that might naturally return you a lat long image, but you want to plot it on a sphere, and you can actually force that to be remapped in other places. And so again, just some simple examples showing what we're doing here. So this is now going to create a 2D mesh grid and plot that, and I'm going to get a nice contour plot like this. And again, as I move my grid around here, I can probe, I can zoom, I can do lots of fun things with it. Similarly with vector fields, if you're sending in the right geometry and shape, then you're going to get this return back 3D vectors. Okay, and if we go to the documentation, this web link will take you to the documentation page on GitHub. It'll go through all the plot types and options and try to give you a good feeling of how you work with those. All right, so let's jump to the next notebook. So now let's talk about functionalizing data, okay? So Komodo is a way to take just raw data and turn it into a function, which means you could interpolate it at any point. This data is not discrete points anymore. It's a continuous distribution of values. So I'm going to create an array of dates here. And you can see that I've created an array of dates. And then I just made a little random plot, which is basically a sine wave with some random noise attached to it. And so here's just the beginning of that file. So now let's define an interpolator, okay? And this is where, again, we're going to make use of other functions. And so we're going to actually read in an interpolator that's part of SciPy, and we're going to define that. And so this particular interpolator actually depends on being a pandas time series for this one, but there's a whole host of different interpolators that we have available in Komodo. And then now if I'm going to go and plot this, you can see that I've now got my basic sine wave with noise attached to it, and that's done that plot of that data set. So I've got this right now, it's a random data set, but I've taken that data set and I pulled it into Komodo. And we can evaluate it anywhere we want, again, by just using that function that we've defined. And so here's an array of times, and you can see that if I'm outside the time range of the data set, it returns me some nans, but if I'm inside, it gives me a floating point interpolation at exactly that time in there. And so again, you can see here's the times, and there's 265 times in here. And so if we call it with no arguments, we get the full data set that we provided it with back, as opposed to giving it an argument that says this is the time I want to interpolate to. So again, we can do our assert, but this is now doing a massive assert where you're taking all the values and comparing it with all the data that we passed it, and it passes that it actually gives you back what you passed in is what you get back out. So now we're going to go to commodifying something. So commodifying means we're attaching some extra metadata to this. And so we've ingested this data now into Komodo, but now let's add some units and citations and other metadata to this. And so we have a function called commodify that will tack that on to our row function here. And so now we've got our row function that's defining these values, and we've now added this metadata to it. So I can look at the metadata, and the metadata I stored says I've given it units. I haven't told it what the argument units are. I've just that one's undetermined at this point. You can put citations, all kinds of hidden arguments that you can set with that. And if you ask for help, it'll actually give you the help module that you provided on it as well, and say, oh, this is density as a function of time. And you can again spit out the raw data as well. So that's just a very simple data set. But now let's jump into where Komodo starts to become really valuable is working with models. So a lot of simulation code put out a lot of output, and it's to be honest, it's a huge amount of data, right? And so we need to be able to bring in this data, commodify it, which means we've got a function we can interpolate in space and time and whatever other coordinate system you want, and be able to read in. And so we have our model, this little simple model reader tutorial that I'm going to go through is going to handle opening and closing files, managing a state variable, initializing some values, setting up an interpolator for it, registering those functions, and kind of what those basic steps are. And so we're going to actually again read in a few libraries here. And I'm going to define now this little my model class. And so in Komodo, you're going to be, so when you initialize it, you're going to have to set a few things. And this initialization handles opening the file, loading in the data into the data set, into this self. It's going to store an XYZ position. It's going to return a density value as a function of X, Y, and Z. And I'm going to use a SciPy regular grid interpolator for this data because it's going to be a nice regularly ordered data. So we'll use SciPy for a lot of our straightforward data sets. Some of our model output can get really, really complicated. And so then we have very, very sophisticated interpolators. And to be honest, one of the biggest ones we have is reading in SWMF output data, which is a block. It's a block tree structure, which means you've got an oct tree of blocks. Within those blocks, you have 8 by 8 by 8 grids of cells that it computes on, and then that whole tree structure gets really complicated to traverse and whatnot, and handling at refinement level changes, like John showed earlier, what those contours changes at the refinement levels. Handling all that accurately is really important, and so we actually have a huge C library that we use for our interpolator for reading in that model data. For this case, we're just going to use a simple grid interpolator. We'll step through here. We'll add commodify here to add some metadata here, and then at the end here, I'm going to say model, which is going to be my Komodo function, is this new model, and I'm going to send in a file name. And so in this case, it's not actually reading the file. That was just a dummy statement saying I'm going to read the file. I'm actually just assigning the file from a space. So the reader is a piece to be filled later. And so the result of that is now you have a new Komodo object which says, hey, I've got this density that's a function of a vector space, so X, Y, and Z, all the units, and then Komodo just returns it as a lambda function, which is kind of a generic placeholder for the stuff on the right, when it's too complicated to actually display what it is. So these lambda functions will keep showing up. So now I can go and register this, and it'll, again, as expected, it'll give me a NaN if I ask for a point outside of my data range, and it'll give me the proper interpolation for points inside the data sets. And so again, you can do the same thing if you're calling it and you didn't actually give it arguments. It's going to throw a vector saying, hey, you didn't pass it a vector of points. You better fix that. Again, multiple ways of breaking this, and you've got to make sure that you're passing it with the right thing. So now I'm going to make a 3D mesh grid of points X, Y, and Z. I'm going to stack them up And I'm going to add some random things, and I'm going to pass these in and make a little plot here. And so what I've done now is created this random cloud of points in 3 dimensions, passed them to this function, and it's actually then calculated what the values of those functions, and it determined that based on what I sent it, this is the right plot type to return. And so you see this is a plotly plot. I can interact with it. I can probe and look at the value at individual points. I can zoom in, I can zoom out. Very handy for analyzing, especially some of these more complex data sets as we get into them. So this is again just calling the built-in plotting function that's part of Komodo. Here it's just saving it to the disk in case there were issues with computing things. So now I'm going to go the next step. Okay, so this actually said I had to provide a set of points or I wasn't going to get anything out of it. But Komodo really wants you to have a default set, which just says, if I want to plot this function, I should know what the range of the value points are. I want to have a basic set of points that says this is the defaults. And so if I just ask for a plot and don't ask for any specific point to interpolate to, I should get a basic plot out of it. And so Komodo wants to have a set of false. So I'm going to now set a set of default points. So again, I've got my similar function. My density here is this lambda function, and I've now got the values of density now have an array shape that looks like this of the values. But now I can actually specify. Here I was actually saying, okay, return all the values for the points that are now defaults. But now I can do a slice and say, well, set z equal to 8 and give me all of the values, all the positions, all of the x's and y's you have available where z equals 8, and give me the shape. And so now you get a 22 by 11 array because you've sliced off the z dimension of this. Okay. Z equal 8 might actually not be some of the default values you give it. It will do the interpolation if necessary, if that's not something you've provided there. And so, well, how do you know that even 8 is in the proper range of things? You can actually import these get defaults, and you can actually look at all the values of z in your data set and show the mean of it. And the mean actually is 8 of all of the data, all the points that I've given in that data set. If you actually take off this, it's actually going to give you all of the data points. Okay. All right, so then our final implementation is we're going to add what we call gridified solutions. So a gridified solution, we've added the IJK variable, which says it makes slicing things in different dimensions far easier. If your solution is a nice regularized grid that supports things in those dimensions, you can actually then provide that and you get a gridified version of it. And so it's again, this is a lot similar to what we had above. I'm defining the same thing, but now I'm registering a gridified, I've self.gridify model of these data sets that I'm passing those same points to it. So what does that actually get me if I gridified my model? I've now got a function density of this vector, but I've also got a density of IJK, and I've got a pressure I've defined now, and I've got a pressure IJK, which is the gridified version. So what does that mean? So if I pass in 258 here on row, that's expecting XYZ, okay? And it's the same thing for pressure. I'm expecting that that's XYZ. But now I've got something that actually can also support an IJK, which you can then slice on, which would come in very handy when we actually can start to do plots. When you get to very large dimensionality of your data sets, being able to fix certain slices with that gridify becomes very, very important. A lot of these have to do with actually developing your own commodified objects. A lot of this is built in right now. If you have a data set and you want to commodify it, we have tools to help you quick pull that in, and we'll get to that later. If not today, then it'll be the example that we work through with Komodo on Thursday as well. So now we're going to combine things. So Komodo as a function can actually build and combine things together. So I'm going to take my basic function here that I've defined, and I've now added another variable to it, and then I'm going to add another variable. I'm going to look at the detail and say, okay, I've defined these, and I've got these shapes. And then now I'm going to, again, use the gridified version of the density, and I'm going to say, oh, but I want to do this slice, and I want the z values, the z to be the mean of all the values, and everything else give me a result. So I got a 2D plot back. So now, because of the dimensionality of what I've sent it, I've now gotten myself a 2D slice through a 3D data set with these using those values. Okay, so that's kind of a fire hose of background. Let's now jump into actually using it for some real world cases. So this notebook here is actually a modified variant of a notebook called Start Here, which is in our tutorials folder in our GitHub. So in our online documentation, we have a tutorial that says Start Here. It'll walk you through the basics. And so this is just a tweaked version of that to show you a lot of the functions now that we've added into Komodo that we can do in the background. So, I mean, the first things we're gonna read is we're gonna load in this model wrapper. I'm gonna read it in as MW, okay? And I'm gonna say, well, and I'm gonna call out of this model wrapper, I'm gonna call choose model, but I'm not gonna give it an argument. So what's this gonna do? This is gonna give me a list of all of the models that we have commodified readers for. So the Adelphi model, AmGeo, CTIP-E, a lot of ITM models here. Gamera is a global magnetosphere model. Space weather modeling framework, the global magnetosphere part of that one is again a large model. But all of these models now have been commodified and are available to plot the output. Again, this is depending, you have the output. There's not a fetch feature in Komodo right now because these model outputs will be often hundreds of gigabytes, if not terabyte of output for some of these simulations. And so we're working on improving that data access part of it. So now I can call this and I can look at the model wrapper and say, well, what's it doing? Well, you can give it a search string. So I'm going to do a variable search. This is a different function. This is a variable search. And the help on the variable search says, what are you going to look for? I can look for variables. I can define a model. I can define a file directory, for example. And so I can set all these things and it'll return what variables are in this model. So if I call variable search and leave it blank, this is now going to spew, okay? Printing all possible variables across all models. So this is now giving me the variable dictionary for all the models. So the Adelphi model has a variable E east, which is the electric field in the eastern direction increasing in longitude. And it's giving you the dimensionality, the units, so SM coordinates and spherical, the function of time, lon and lat, it's giving it its units. This is just a host of metadata of all of the model outputs. And it goes and goes and goes for all of these models, all of these variables that are available to be loaded and visualized. Okay, get past that. So let's do a subset of that. That was too much information. Let's look for just what has temperature. Okay, well, this model doesn't have temperature. This one doesn't have temperature. Well, CTIP-E has several temperature variables in it. Ion temperature, neutral temperatures, temperatures that are a function of pressure level. Over here, temperature is a function of height. And so there's a few variables that have temperature as the output variable and a number of them that don't. And so we'll get to examples where we're actually sucking the temperature out of some of these models. But now I can say, well, I want to just look at temperature for CTIP-E, and it'll just give me the results for that one model. I'm going to skip this cell. This is going to spew all the variables for CTIP-E again. So we've got readers for a whole bunch of models, and they've got a lot of variables in there. So now we're going to actually start to load some model output. So I'm going to start with a CTIP-E run. This data is currently stored on the Scratch space here on our cloud, and there's different ways of setting it. If your data is stored in an S3 somewhere, you can give it the URL this way. If it's on your hard drive, you can give your data this way. So you're going to define the file directory, which is where your data is sitting at. So now I'm going to do a variable search for the CTIP-E model in this Scratch directory that I've got here. So this says the data set that I have has these variables in it, because that previous list that listed every possible variable that the code might ever output, but not every run is going to output every variable. And so this is actually saying for the data set I have all these variables available. There's quite a few of them there. And so again, I can search for what temperatures are in this particular data set. And I can look for what time ranges I have. And so for this particular data set I've loaded, I've actually got about 5 days worth of data here stored, downsampled a little bit in size to make it fit here. And so there's all these probes. So we've got a chunk of data, and this data is sitting here. So now let's import the right reader for that. And so model has been defined to CTIP-E, and so we're going to define the reader to be the reader for CTIP-E. And so again, we've got help on the reader and what arguments it has to have and what arguments are optional. Close that. All right, that's going to spew for a while. In general, too much documentation is better than too little, but sometimes it's a pain to scroll past. So now I'm going to actually define a Komodo object based on the reader, and I'm going to point it at the file directory. And so it's going to read that data set, and this will take just a little bit here. It's going to actually read the files off the disk, and it's going to go through reading that data set. It's going to scan the data set. It's going to read it. It's going to commodify it. It's going to create all the metadata it requires, create the interpolators for it, and it's going to be at the end. It's going to show you then the LaTeX list of all the variables here. So now here's a list of all the variables that I loaded in, and so now I've got variables that convert from pressure levels to actually altitude in kilometers. So there's some conversion factors there. Densities, temperatures, pressure. So all the variables that I showed before, and some of these are very sophisticated, again, to get the units the way they ought to be. Conversion factors were all taken into account to make sure that these match the units that we want the output to be in. So it's read this data set now. And I can look at the details of that, because sometimes if you look at these variables, you got to type these once in a while in Python. And because these are rendered in LaTeX, sometimes figuring out what that started out as can be a pain. So to realize this is H_ILEV1_IJK is you can actually pull out those detailed bits of information, which does come in handy. But again, that gives you a table, 124 variables that I read in for here. All right. So now I can do the same thing where I can turn the gridded information off. This is going to reread it in again. And this is basically going to create fewer variables because I'm not creating some of the gridified variables. Let this go again, some of these options. And I'm going to read this one because I need to have the Komodo object too for the next plot. So now I'm going to load in just the neutral temperature and and the ion temperature here. So I'm just going to read just those two variables. And you can see that I only asked for two variables, but I still got a few others because I still have to do these various conversions between pressure levels and altitude to be able to get the variables where I want. So even though I only asked for a very simple variable, I got a few others that came along for the ride. Again, I can do the same thing by turning various options off. I can turn gridded off, gridded true, and a variety of options here. I'm going to execute these just to make sure that I don't use them down below. So now this cell right here, this file date, Komodo does something unique with its conversion. It needs to know midnight of the first day of data that you're reading in. And then its interpolation is based on hours from that point. And so to do that interpolation. So this file date time is going to be important when you're doing some of these plots. And we're actually going to give time. You can see down here, time I've given it 22.5 hours from this initial file date. So I've loaded in these data sets. I've loaded in these two variables. Well, what's the range of values for these variables? And I can see that time has 480 times that I've read in here. Hours is going to go from 0.25 to 120 hours. Longitude, there's 21 longitudes in this range, 91 latitudes, 17 different heights in my grid between about 80 kilometers and 500 and some kilometers. And similarly for the ion temperature at different altitudes, because this model has different grids for different variables, which is another issue that Komodo is designed to handle. So now I'm going to ask for a basic plot. And so I've got this plot. I'm going to do a plot of this variable. I'm going to do the gridified version, which is IJK. And then I can give it this plot partial option. And again, this scrolls off the side. Now this variable is a function of time, longitude, latitude, and height. And so if I say, well, fix time at 22.5 hours, fix height at 350 kilometers, that means the other two variables are left to float. And so by passing that as an argument, it's going to have to do a quick pressure inversion at this particular interpolated point in time, because the 22.5 might not be one of my times in my data set. So it's going to do an interpolation in time to get those values. It's going to interpolate in height. And then now I'm going to end up with a plot of longitude, latitude of the values at that time. And so it's done that slice. Now, that's a very crude default plot, and the default plots often are very, very simple. And so we've added some extra little thing called figmods, which allows us to adjust colors and scales and some of that. And so we can actually get a plot that's much nicer, much what you would expect. And so these are just very small tweaks. We've seen other packages that have these options to modify the plotting to get the description the way you want it to look like. And so now I have a plot that's in a nicer color scale. It's got a better labeling on it. And here's the value. And I can zoom in on a box, for example, and see what I want to see. I could ask for multiple variables. So that a plot object, I can ask for both the neutral and ion temperatures at the same time. Again, with a similar slice. But now in this particular one, if I scroll to the right, I've actually set time, lon, and height. And so now these are going to be a function of just latitude. So this is now temperature as a function of latitude for a specified longitude and time. And so this is now the plot so that you can look at the, I didn't need to click that. Plot scrolls off the right, yeah, right. They fit that. So anyway, we can look at those two variables and see that. Now, Komodo can also do really simple point probing. And so I can jump through and just call this object and say, at this temperature, I want to send these 2 points at it, and I want to get the value. And it's giving you the value of, I just gave it two sets of points. I can do a similar thing where I'm calling the gridified version, and I'm setting an array of times and then a fixed longitude and latitude, and I'll get, again, those same two values back out of here. These types of functions will become really important because we'll be able to do things like satellite fly-throughs of the data. So you have a 3D data set. You can say, I want to go and fly goes through this data set and give me the values, and it'll go and send it these array of points and get back and do all the interpolation in time and in space. All right, so let's do a little more complicated example. And I'm going to do an example that's going to look at 3 readers. So now I'm going to actually take models. So this is going to read in CTIP-E, it's going to read in GITM, and it's going to read in WACA-MAX. Those are 3 different ITM models. I'm going to read in those results that I've got here on the disk. I'm going to skip looking at all the variables, temperature, but I'm going to look at this and say, oh, okay, the CTIP-E has these temperatures in it. Okay, that's fine. So I'm going to actually go ahead and read, and I'm going to specify the neutral temperature and the ion temperature, and I'm going to read that into this Komodo object. And so now I've read in this object, and I've got these temperatures available. So I can do the same thing for GITM. GITM does have some temperature variables. It has just one in its output. So let's go ahead and read the neutral temperature from GITM. Same thing with WACA-MAX. I'm going to look at WACA-MAX. It has a few temperature variables. So I can go ahead and read those temperature variables out of WACA-MAX. Now I can then, I've created 3 separate Komodo objects: Komodo object WACA-MAX, Komodo object GITM, Komodo object CTIP-E. But Komodo objects can again be combined and mixed and matched. So I'm going to make a new empty Komodo object, and I'm going to copy the temperature variable from CTIP-E, from GITM, and from WACA-MAX into this new single Komodo object. And so now I've got a new Komodo object, which is just those 3 variables in it. Again, I can look at what are the coordinate ranges, what times, lon, lat, height ranges, and say, okay, the height here is 75 to 379 kilometers, 96 to 592, and basically 0 to 600. So if I'm going to do a slice, I want to pick a slice in altitude that fits within those here. I can do the same thing. I can look at the time, the date, the file dates, the start times. So they all start at on the same day, and so I can set the times the same. So now I can let's look at a plot. I'm going to first look at CTIP-E and just look at CTIP-E, and I'm going to do a plot, and I'm going to do the plot here at 12 hours height, at 12 hours into it, and a height of 300 kilometers. So this is going to generate that plot. Here we go. I've got my default plot here. Again, I could do the same thing with a little nicer one. I'm going to skip that to save a bit of time. I can do the same thing now. I can slice through various dimensions. And so before I'm going to slice now at a fixed longitude and latitude. I'm going to pick a point in space. And then what it's going to give me back is it's going to give me time versus altitude, because those are the other 2 unset variables. So this is time in hours through the simulation, and these are the altitudes. And you see that CTIP-E actually has, because CTIP-E solves in pressure levels, the altitude will actually vary when it interpolates that as things go on. So as you see this enhancement here, the altitude is actually going to be pushed up to a higher value. So it's interesting to see how that works. I'm going to do the same thing with a GITM plot, and it's going to load GITM. One thing you'll notice here, it says time slice added to file. Komodo does what we call lazy reading. So some of these data sets can be really huge. And so it only reads the data that you've requested. So if I haven't asked for all these times, it's said for the time I've asked for, I need to grab this file and this file because the times between those 2. It'll only read those 2 files, do all the interpolation and plotting, and it saves quite a bit of memory in working forward with these things. So here's this plot now of a slice for GITM. Now, the third model in here is WACMX, and WACMX output is absolutely ginormous. And when I first set up this notebook, I had these commands down here below. It wouldn't fit in 8 gigabytes of RAM on HelioCloud. It turns out that the final version of HelioCloud that we have has 12, and so it does just fit. So I'm going to actually do this and see if the memory actually fits. And I'm going to go down here. And I'm going to actually then now do a slice. I'm going to pick 12 hours. I'm going to pick a latitude. I'm going to pick a height. So this is going to be a plot of all the longitudes and the temperatures at that range of longitudes. All right, so we're going to go through. It's going to convert some pressure levels. It's going to read some slices of data. And if this all fits in memory, which it tested before, boom, here we go. Now this is now a comparison, all 3 models. And so here's GITM's temperature, here's WACMX's temperature, here is CTP's temperature. And you can see even the time scales are very different. There's a lot of points here along the WACMX. It's a very fine grid. It's a very coarse grid here for CTP in longitude, and it's kind of in the middle here for GITM. So we can now do these model comparisons and look at them. Again, like I showed before, there's lots of interpolators here that we can do, and so you can actually just call interpolators in lots of ways. I can actually just do this dot notation and pass in a point and get a value at that given space and time. I can do the gridified version where I actually define those variables and get the same value out. I can do it for different variables. I can do a lot of interesting things. This particular one here, I've actually said, well, let's look at the pressure level grid and say, well, I want to look at 350 kilometers altitude at a given point, longitude, latitude here, but what does the pressure level correspond to that? And so you can look at the pressure level, and you can actually do a plot of that and say for a given position in space, how does the pressure level vary? So the pressure level varies up here to above 14 to down to about 13. So you could actually look at different ways of slicing through pieces of this. All right, so now I'm going to jump down to a different notebook, and this is the Komodo data model comparison. And I added this one last minute because I wanted to kind of tie in how we talk with other packages a little bit. And so there's different ways of sucking in different types of data. I want to show how we're using Happy for some of this stuff or some other little APIs. And so we've got Happy has been wrapped in a Komodo shell. And so it's the core Happy that you were demoed already, but it's got a Komodo wrapper around it so it knows how to handle that. And I'll show that down below. But we've also written a little function called for a SAT extract, which basically can take, it talks to a little API server at the CCMC, and this will be changing, but they're changing at some point in the near future. But for CCMC, we have a very large group of run-on-request simulations that are available. And so for this particular run, it was a run that was submitted about 9 years ago that simulated a storm in 2006. And this particular run has a bunch of satellite extractions that have already been pre-computed for it. And those are all sitting there on the disk that we can load. So if I say I want to load GOES-12 data in GSE coordinates from this run was an SWMF run. I've now loaded in positions and the standard MHD conserved variables plus currents that are available. So these are all variables that are extracted along that satellite path from the model, and I've now got them in this little Komodo object. And so I can go in this little Komodo object and I can make a plot of the magnetic field. And let's think for just a little bit. I might need to close some of my previous notebooks to save memory. Let me Do that a minute here. Oop, it's totally hanging up now. Oh, there it comes. Okay. So here's now a plot of the three components of the magnetic field extracted along GOES, but simulated by this SWF run, okay, for this time period. Now I used a special little add-on plot called getPlot. This is a unique little add-on. It's not the standard default Komodo plotting. I could do this same plot as a standard plot, but then building up this version with X, Y, and Z components of the field is just handy to do it this way. And then one of the other options you have with this is we can do some fancier 3D. Like I said before, these are all line plots. You've got position is just, position is a function of time, or magnetic field is a function of time. These are all nice time series data. But sometimes you want to visualize things in a little more dynamic way. This is another way of looking at that. This plot has a weird skew to it, but this is now the values of the magnitude of the magnetic field along the path of GOES, and then the magnetic field vector is shown on top of it. And I'm going to tweak this plot a little bit to try to make it bigger. And I'm going to do that. Let's see. Because these are plotly objects and they have lots of little nice features I can do. Let's see. I'm going to adjust the height and make this image a little bit taller, so that it should display better on this zoomed window. So it's pre-computing it. If I had saved this image, I could have just applied that update to it without having to recompute it, but because I didn't. So now I can actually see, here's the day one of the data, what the magnetic field looks like on GOES. I can go down to my slider, I can jump to day 2. And you can see at this point, it's cruising around just nice and quiet here. And then the storm hits and you see the magnetic field jumping and the magnetic field vectors becoming much more disturbed as you go through here. So you can slide a time slider across the bottom and you can slide through. And there are many options you can give to this plotter. I've said group by day. I could be grouping by hour. I could group by orbit. I could do a variety of things. This gives me a nice interactive view of what's there. But now let's look at what we've got with our happy version of the same thing. So we're going to set these same variables, which are very similar to what you saw before. I'm going to grab the same start and stop time that I have from the simulation, and I'm going to ask for magnetic field values in GSE coordinates for this data set. And so I'm going to grab that from C.Web with a happy interface. And I'm going to do the same type of plotting, and I'm going to plot the magnetic field vectors. And this is now data from C.Web for that same time period. But now let's go to data. Let's say what we can do to data model comparison. So we can actually take this happy data that we've loaded for the GOES satellite and dump it into a new variable in the run and request Komodo object here. Now I'm going to do a little time interpolation to make sure these are on the exact same time scale. So I'm going to make a little array, which is basically the times that are available. So I'm going to take the spacecraft time cadence and interpolate all of the run and requests to that same time cadence as well. So it's a little interpolate function. I'm going to calculate a little delta, and so I'm going to now compute a little difference function, which is the difference between the two. I've now created a new little time series. I'm going to dump that into functionalize that into my data set and add it in. And now I can do a plot. I'm going to ask for a plot, which is this is the simulation BZ. This is the GOES 12 observed BZ, and then this is going to be the difference plot. So now I've got a plot where I can actually look at what those values are, and you can actually. Oops, I zoomed in again, unfortunately. That clicks on me too quickly. All right, and that is too hard to zoom back out because my controls are just off the side of the screen. So it's asking easier just to recreate it a second. But you can now do a data model comparison plot, and you can see this is actually the ghost data is here in red. The simulation output here is in blue, and then the difference between those two. So you can do a lot of different science analysis with these tools here. And so this is yeah, I think that was the last notebook I had. Now I was going to do just a quick well, before I go a little farther, are there any questions on what I've done or how it's used? Because then I have one more kind of new twist that we're adding to things in a little bit. Okay, I'll jump forward here. All right, so there's, oh, yes, it did. Okay, so we have at the CCMC, I've got parts of Komodo online. And so some of these models that I was showing you, like CTIP-E, I can jump and look at a visualization through a web browser. I talked about how Plotly is nice about generating images for a web browser. And so here's a list of CTIP-E models. If I go to this default visualization, this is the normal landing page for this run for the CCMC to land there. And there's a little link here that says view output in Komodo, right? That's the same as the page I showed before as viewing the output in Komodo. So I can click on that and it'll bring up this page. Let me zoom in a little bit on that. If the image had been previously requested, it'll show it automatically. But now I actually have a nicer version of the list of all those variables. Description of the variable units. You can see that it gives you a range and says, well, these are what I could look at. And I'm going to pick a time. I'm going to pick a height. It'll let lon and lat float. It's a 2D plot. It's going to show the continent shorelines. This is then the result. And you can see that I zoom in and I can actually look at the values here online. Now, this is a nice tool for looking at things, but one thing that makes it nice is we also have this view Python script used to create this plot yourself. And so if you have your own notebook and you have the data set yourself, and so your own path to the data, if you actually run this little Python script, it's going to actually create that exact same plot. And so you can see it's importing Komodo, it's setting a few local variables, it's calling the reader, it's going to read in the variable I've requested, it's going to make the plot, it's going to modify a few of the color scales on it, and then it's going to actually save it to an HTML that you can load and visualize and interact with. And so that's kind of a neat little online way of looking at some of our visualization. Let's try this one too. So I'm going to show this one, which is actually a prototype page. So John showed a little while ago the SWMF output and looking at slices and looking at some of that data. And so I've been working on, again, some of the same thing. And we're working on a way to visualize this in 3D. And so this is now using Komodo to generate a visualization in 3 dimensions of output from the space weather modeling framework. And so in this particular case, I can choose which slice I want, where it's at, which orientation. I'm extracting, again, there's some graphics glitches drawing here. I'm extracting the bow shock surface, which I'm computing from the 3D data set. I'm extracting the magnetopause boundary. I'm actually flying Themis A through here, and on the bottom, here's MMS flying through here, so you can actually see when MMS cuts through the bow shock in this simulation data. And so there's new ways, and this is something that at the CCMC, probably within the next few months, we'll have online tools to use Komodo on the back end, but to provide fancier 3D visualization for some of our simulation output and going forward. So this is using Komodo to do this analysis and this visualization there. I think that's about the end of what I have. If there are any final questions, I might save you a couple of minutes of time here. Is there anything online? So on Thursday, I'll be doing a tutorial with Jonathan on tying Komodo with PySat and trying, again, showing how those tools are compatible. Komodo, it makes use of a lot of tools. We read in SpacePy, we read in happy things, we read in things from other packages. And so there's a lot of collaboration that goes on in Komodo and talking to other packages and pulling things back and forth together to try to both analyze them and visualize them for scientific output. So, all right.
Thanks, Darren. All right, since we were supposed to end a little later today and you finished a little early, let's still just take a 15-minute break and then come back a little sooner so we can get out a little sooner. I'll put the time up on the screen. No, I just definitely messed up my Excel. Okay, I'm gonna check accidentally, like, each like beginning for start time is equal to like the last cell. Yeah. Anyway, okay. Cool. It's gonna be for you. Oh, wait. Testing. All right. Now, testing. Okay, cool. All right. Last up for the day, we have Madrigal Web, and Catherine will be presenting on this.
So howdy, folks. My name is Catherine Cariglia, and for folks that don't know me, which is probably most of you, I am an undergraduate student studying computer science at the University of Massachusetts in Lowell, and I've been working for, oh, let me get my slides. That would be good to have. And I've been working the past few years at the Haystack Observatory over in Westford, Mass. Been working there since I was in high school, actually. And today I will be talking to you guys about another very useful tool for both atmospheric science and heliophysics, the Madrigal database. So before I start talking about Madrigal itself, I'd like to give a brief introduction about CEDAR, which stands for Coupling, Energetics, and Dynamics of Atmospheric Regions. So CEDAR is a research community investigating the near-Earth space environment. And for folks attending this year's workshop in San Diego, I will see you there. So Madrigal stores a variety of upper atmospheric data from various ground and space-based instruments all over the world. And the Haystack Observatory Atmospheric Sciences Group maintains the Madrigal database. Additionally, Madrigal is part of the Millstone Hill Geospace Facility, which is supported by NSF. So now getting into Madrigal. Madrigal is a distributed database which is installed at various sites all over the world and has a central archive at the CEDAR Madrigal database. Data at each of these sites is controlled locally, but they share metadata for easy data access. So the CEDAR Madrigal archive also backs up all of this data on a weekly basis to speed up the searching mechanism. So say, for example, if you were to search for GNSS total electron content data on the iSCAT site, you will be automatically redirected to the CEDAR website. So more about the data in Madrigal. Madrigal has a huge variety of instruments and various different data types, currently at least 200 instruments and more to come, including but not limited to incoherent scatter radar data, lower and middle atmosphere radars such as MF and MST radars, photometers, Fabry-Perot interferometers, DMSP satellite data, etc. Our most popular data sets, of course, are the ISR data, the DMSP satellite data, and most importantly, the GNSS total electron content data, a summary plot of which is pictured here. Of course, it's good to be able to visualize your data sets. So we try to include these summary plots for all data types. And we work with the PIs to customize these summary plots for their data and their instruments. So Madrigal is, of course, open source, both the database itself and the API. Currently, our version control system that we use is Subversion, but work is in progress to migrate this over to Git and GitHub. You can download or update Madrigal if you already have it installed at this link here. So how do we store data in Madrigal? So for a single file, the underlying data format is HDF5, and it comes with very well-defined parameters with standardized descriptions and units. And all of these parameters have corresponding uncertainty parameters to determine the accuracy of this data. Additionally, these well-defined parameter standards allow for the existence of a derivation engine to calculate a variety of parameters you may want to see along with your data given a geographic location and a date time. So the data provider doesn't necessarily have to include those parameters, and that's why we have the derivation engine. So in this structured HDF5 file format, again, all of the data is generally self-describing with all notes and definitions included. The table layout is given for every single data set, and the array layout is the default option if any independent parameters are given. This array layout can be disabled if those independent parameters are non-repeating, meaning that the array would be too sparse. So I guess as a brief visual example, I can just to show the difference between table layout. Say if you were to look at TEC data, you'd have the latitude, longitude, TEC. And in the array layout, you would have more of a two-dimensional grid. You'd have latitude, longitude, and TEC. And for this side of the room, like you guys can see it over here. So hopefully that helps clarify that. So how do we store all of this data in the back end of Madrigal? As far as categorizing the data for each site, the top level of the metadata is the instrument that and all of the instruments that any site has available to it. The next level of metadata is the various experiments associated with these instruments, of course, which have a limited duration and a single PI contact. And then within these experiments, there are experiment files, which is data from one analysis of this experiment, typically over 1 day of data. And of course, in these files, there are measurements over a single period of time, which you can use for your analysis. So what formats can users get Madrigal data? Of course, because the data is stored in HDF5, you can also output this data in HDF5, but we also allow you to export the data in netcdf4 or ASCII format if you'd like to use any string parsing mechanisms. And all output formats contain both observed and derived parameters. So before you use Madrigal, and especially before you use Madrigal data in a paper or talk, please contact the PI. The PI for every experiment is listed on the data download page, as well as it's accessible via the API. Contacting the PI is very important to, of course, give acknowledgement, but also the PI can help you understand the data and what it's supposed to represent and any quirks that may exist in the instrument itself. For example, I believe there was an instance not too long ago where someone wanted to use data from the Millstone Hill ISR without realizing that it has both a vertical and a steerable antenna, which does low elevation sweeps. So this user expected the data to be strictly vertical, but used the steerable antenna data and thought the data was junk. So if you contact the PI first, they can help clarify any of these nuances. So don't let this happen to you. So using Madrigal, there are two main methods you can use. You can either use the web interface, which is best for discovering new data types and instruments, or you can use the Web Services API, which is available in Python, MATLAB, and IDL. So first, I will give a brief demonstration of the web interface. So let's make this bigger. So here I am at the Cedar Madrigal homepage. And first I will show you just a simple use case for looking for various types of data that you may want. We'll start by listing some experiments. Oh, and you have to give, this is for unverified login information, just so that PIs can see who is accessing their data. Pretend I spelled that right. All right, so let's look for incoherent scatter radar data from our good old Millstone Hill IS radar. And we'll just look for experiments from this year. And voila, you can see all of the experiments that we've done at the Millstone Hill ISR radar this year. You can go to any one of these, and you can select any one of these experiments and see more information about the instrument itself. Or you could select a single experiment from these experiments. Oh, it wants my login information again. Okie doke. So we'll look again for some more ISR data. Make this visible. Go back here. And let's see. Yeah, we have one experiment available for this month. A couple, actually. So here we can see our long duration run, and the PI information is listed here. You can select whichever of the available files you would like. Let's see this one. And you can download the file here and select various parameters or filters that you would like to see from this data set. Additionally, you can find some plots and additional documentation here, or print the file in an ASCII format. And if you wanted to get other output formats, you would just pick one of these here. So here. So now a little more about the API. With the API and also using the web interface can generate commands which you can then run after having installed the API to automatically download any data you want much faster than the web interface, because it downloads all of the files one by one instead of you having to type in which files you want one by one. And additionally, there's greater flexibility for data filtering and inclusion of derived parameters as well. To install the API, most users simply use pip, or you can download the source from this link here, as well as the MATLAB and IDL source if you so choose. So there are a variety of things you may want to do with the API, and using the web interface to generate download scripts is one of the simplest use cases. So you don't even really need to read the documentation for that. If you just want to download a lot of files, you can just use the global download method. If you want to download filtered data, you can use global ISPrint, or if you'd like to customize your own script, you are more than welcome to do so. So more about those download scripts. Here I just give a brief overview of the options available to you. But now I can actually show you that here. So let's go to Access Data and create a command to download multiple experiments. So let's first see if we can get some data as is, get some more ISR data. Here we go. In Python from this year. Oh, extra one. And you can additionally pick which types of data you'd like to see here. Let's get our plasma line densities. And we generate the command here, which you would then just run it in a terminal or something. Or you can create a command to filter your data. Show that here. Again from this year. So get some time parameters because those are always good. KP index is also good. So you can see also all of the parameters which you can get for this data, including derived parameters. So let's see, what else should we get? Let's get our electron density and our error in electron density. Can have some additional filters here. You can set limits for the data as well. Let's say, just as a very simple example, where's our KP index? Here it is. Let's say KP greater than 2. And voila, now you have a command to automatically download all of the experiment files in this time range with these filters applied. So let's go back here. Yes, and now I can showcase a bit more about the API. We'll just go through a very simple example. You can download the IPython notebook there, or you can just get it directly from the HelioCloud interface. So we'll get started. Of course, here's another link to access this notebook. Here's a link to download Madrigal and the API. And just if you want to, just install Madrigal Web with pip. And here's the link to the CEDAR database, some tutorials and some references. And if anyone has any questions, just email me here. First, we can just import our Madrigal Web library, lovely. And then we create the database object, which we will use to connect to any Madrigal site. Here, we just use the CEDAR site, but you could also use any of the other sites, including iSCAD or the Millstone Hill site, or any of the other sites that are in Madrigal, or that have a Madrigal database. So to access this data, again, the top level of metadata at any site is the instruments that are available. So you can list all of those instruments with a simple call to the database object, get all instruments. And this list is quite long, so I'm not going to print it here. But each object in that list is a Madrigal instrument object, which has, of course, a name, a code, a 3-character mnemonic, and location information, as well as a category describing which type of instrument it is. And you can use these attributes to search for instruments matching your criteria. For example, you can search for magnetometers in the southern hemisphere with a few simple NumPy mechanisms. First, we pull the categories of those instruments. We get the latitude for those instruments, and we get the indices of the instruments where magnetometer exists in the category and the latitude is less than 0. And here we print the first instrument in that list, which happens to be the Hikamarka magnetometer. And we have some lovely information about its attributes. And notably, the code here associated with the Heliophysics magnetometer is not related to its position in the list. And this code is referred to as the KINST, or the instrument identifier. And this will be used for the rest of the calls in this notebook that refer to this instrument. So going down in the levels of metadata, of course, the next level of metadata are the experiments available at any instrument. So we can easily get experiments for an instrument given the instrument code and a date time range for which we would like to see data. And you just pass those arguments to the get experiments call for the database object. And let's see the first experiment in that list. And we have information about this experiment here. So list the URL which you can find this instrument at, the time instrument, or the time data for this instrument, time range, the PI name and contact information. And here I list out just some more details, general details about experiment object attributes. And similarly, compared to instrument objects, you can filter these experiments, say by keyword in the experiment name. And again, going down in the levels of metadata, the next call that we will show is getting the experiment files for this experiment. So we just use this simple call here to get the experiment files with the ID of the experiment, which similar to the KINST, doesn't relate to the position in the list, but it's just used as an identifier. Any experiment may contain several different types of data and will be described in the kind of data description or KINDAT desk. So here, and this is another one of those attributes in a Madrigal experiment file object, which you could similarly use to search for any particular type of data that you would like. And additionally, in the API, you have accessible a citable DOI, which uses a W3ID redirect to have relative permanence. So this link should exist forever. And this link points to exactly the type of data that you have referenced. And if the experiment is ever updated in the future, this link will still point to the original version of the data. So you don't have to change any of your publications that use that data. So a bit more about experiment file objects and their attributes. And of course, yeah, you can filter by the type of data here. And now we can test downloading this data. So as I showed previously, you have to give some little identification information, but of course, this is not verified. So you could actually just use this example here and it will still work. Please change it to your own information though, so that the PIs can see who is using their data. So we download that first file that we were looking at with the call to download file, and we pass it the name of the file, the destination and name where what we would like it to be, and our user information as well, and whichever format you would like. And you can even see the types of parameters in this file with a call to get experiment file parameters and the file name. And there are, of course, lots of parameters in the file because of the inclusion of the derived parameters. So I print the 45th one in the list, which happens to be the variation in UT time. You can also simply print the records in any file in a simple ASCII format to use any string parsing mechanisms you would like to filter your data with a call to simple print. So we pass the file name and your user information. And here I'm just printing the first 1,000 characters just so you can see what that looks like, but you can certainly make this much prettier for all of your use cases. You can, and of course, as I showed with the web interface, you can download any file with only the parameters you select using filters to remove any data you don't want to see. You can find a list of all valid Cedar Madrigal parameters here, which includes units and descriptions. To filter this data with the API, you need to write a filter string, which is comma delimited, but you can see a simple guide for how to do that at this link here. So for our little simple example, we'll get we'll use the Heliophysics magnetometer again, the same file we were looking at, and we'll pull our date time information and the north, east, and downward components of the geomagnetic field. I'm just going to apply a very simple little filter to limit the northward component between these values and the eastward component to be greater than this many Teslas. The filter string then looks like this, where the blank over here in the eastward component part of the filter string denotes no upper limit. So here's our filter string, our desired parameters, and we use a call to isprint with the file name, the desired parameters, our filter string, and our user data. So we can get our result here, and we can just pretty print the first 5 lines, and voila, here is our filtered data. And you can easily plot Madrigal data using most of your favorite plotting packages. We usually use matplotlib just because it's very customizable. And for a very simple example here, I'm just going to show a time series plot of the northward component of the geomagnetic field, which we just pulled from that file. And using the HDF5 format and H5Py, we can just pull these data sets here, which generally behave very similar to NumPy arrays. So you can pretty much treat them as such. And here I just make a list of date times. You could do this in a much more straightforward way, maybe by using the Unix timestamp. Get some label formatting here, so the date times don't overlap. And here's our lovely time series plot. Obviously, this is not publication quality, but it's just a simple example to demonstrate how easy it is to work with Madrigal data. And other tools available in Madrigal. So Mad Calculator is basically an API interface to the derivation engine, which can calculate the values of any requested parameters given a date time and a location range. So, of course, it takes a date time, start and step latitude, as well as longitude and altitude, and the parameters you would like. And you can specify exact values which you would like to be calculated for those parameters, but we'll leave that out for this example. And the result is returned as a list of lists of doubles, where each list has the point in space-time for where the value that you wanted to be calculated was calculated. So, and if the value can't be calculated, it will be set to not a number. So we will be testing the Mad Calculator service using the geomagnetic field strength and the northward component of the geomagnetic field, just as a simple example. Just get this day in February 1999. Just a couple points of latitude, a couple points of longitude, and static altitude. And here we go. We pass this to Mad Calculator with our date time information and our geographic information and our desired parameters, again, a comma delimited string. And here we can see these results. So we have our point in space information and the two parameters we calculated for each of these points that we have specified. So another tool available in Madrigal is the Trace Magnetic Field Service, which provides a sort of similar functionality to what was described earlier in the PiSpeedAS and SpacePy tutorials regarding tracing the magnetic field. And it can trace to a it returns a point along the field line for each point that you specify in a very similar manner to Mad Calculator. And you can trace to either a conjugate point, an intersection point, etc. And it uses either the Tsyganenko or IGRF fields, depending on which model you specify. You can also specify which input and output types you would like, either GSM or geodetic. And here I list just the list of arguments that you could give this function. And the result is, again, returned as a tuple of tuples, just another sort of a list of lists. One tuple for each point in space, and returns either the geodetic information or the GSM information for each point. I'm gonna test with these following arguments. We just will test this particular day in March 2010. We use geodetic as input and output type. We use this range of altitudes, single latitude, single longitude. We use IGRF and the north out qualifier. Let me stop here. So, and we pass these arguments to trace magnetic field, and here we get a couple of points given those parameters. So I think folks more familiar with tracing the magnetic field would find more use cases for this. So I hope that's useful. Now let's get back to my, what was it? Okay, so again, more about the derivation engine. So the standardization of the file parameters allows for the existence of the derivation engine. Again, all these parameters have corresponding uncertainty parameters, so you can always know how accurate these calculations are. The independent parameters for any data are built into the standard. All the derived parameters appear in the file, and the derivation engine itself can determine which parameters are able to be derived. New derived parameters are relatively easy to implement in either C or Fortran, and work is in progress to get more derived parameters available via Python. So now I'll just briefly show you what the derivation engine interface looks like through the web. So we can go to Run Models, run the Madrigal derivation engine. Here you can see it's just an interface to the Madrigal calculator, and it's a bit better to look at than the API. You can specify the start and delta geographic information, the UT time, and here you can see a big long list of all of the parameters that you could possibly derive. And then you can just simply calculate. So just a brief overview of those derivable parameters. You could get various space and time information, including local time and shadow height, various geophysical parameters, including the KP index, magnetic parameters, again, such as the geomagnetic field strength, and modeled data, including MSIS data, which is a neutral atmosphere model, IRI data, which is the International Reference Ionosphere model, and other modeled data, including the North American Total Electron Content model and the empirical ISR model, which was developed by my esteemed colleague, Dr. Shenrong Zhang, over at the Haystack Observatory. So, all right. For any PIs in the audience who would like to get their data into Madrigal, there are two methods available to you. You could either send data directly to us folks at Haystack, including documentation and summary plots, which we can automatically generate for you. We will write a loading program, which you will then verify the accuracy of, and you can choose to either add new data in batches or via an automated upload. Alternatively, you could set up your own Madrigal site, which we will help with installation and creation of loading programs, but you get to control when the data is uploaded. And all the data that you do upload will be automatically backed up to the Cedar Madrigal site. So going forward, there are a number of things on my to-do list, including but not limited to importing Madrigal from the Subversion repository over to Git and GitHub, including unit testing for Madrigal, the database, and the Madrigal Web API, making Madrigal Web conform to the Heliopy coding standards and hopefully future integration with Happy. Python implementation of derivable parameters so we can move away from C and Fortran wherever possible, including geographic bounds of experiment data in the metadata, which would help to support the space metadata model or data model. And the work for that one is mostly complete and will be included in the next release of Madrigal. And additionally, making Madrigal Web available via Conda, so you don't have to pip install every time. All right, so I think I'm a little bit early, but thank you all so much for listening. And thanks so much to the organizers of this workshop for supporting early career folks such as myself. And if you have any questions, I don't believe there is currently a place in the Slack for Madrigal Web. So just email me directly if you have questions. Are there any questions I can answer currently or?
Not a question, but you do have a space Madrigal Web.
Oh, I do. Okay.
It doesn't have dash. It's just one.
Okay, cool. All right. Okay, but right. So.
All right. Well, that brings us to the end of today. Again, if you have any other questions that you think of later, just to get to ask during presentations, there's all of the different packages with their separate channels in the Slack. So you can go there and ask whatever you're thinking. Tomorrow, we're going to be switching it up a bit, having some information on time and coordinates within PyHC and widely used packages, some how-to sessions on important things you might want to know, being a programmer in open source science, and some posters and panel session. Also, if you're interested, myself and a few others are going to be heading over to Avanti just for some, after day chilling, hanging, talking. They have really good drinks if you're one who partakes. So thanks.
Nice shot.